Hello and welcome to Sleepy Science. What if the world around you is not the simple, solid, silent place your senses tell you it is, but a hidden system of delays, invisible forces, recycled matter, biological illusions, cosmic leftovers, and quiet processes happening beneath awareness every second? What if your eyes show you less than your brain pretends? Your memories change as you recall them. Your body is rebuilt while you still feel like the same person. And even the water you drink has been moving through Earth for billions of years. In this journey, we'll move gently beneath the surface of ordinary reality. From the strange way your brain creates color, touch, silence, and time, to the ancient iron in your blood, the invisible ecosystems on your skin, the moon stabilizing Earth's tilt, and the sun slowly losing millions of tons every second to keep the world lit. These are not myths, exaggerations, or fantasy facts. They are real scientific truths hiding inside the everyday world. The kind of truths that make a simple breath, a blink, a glass of water, or a beam of sunlight feel suddenly deeper than before. So if you're ready to see the familiar world become unfamiliar again, tap like, hit subscribe, and drift into the mystery with me. Because the deeper we look at ordinary reality, the more it begins to feel like the universe has been strange all along. And your senses were only showing you the easiest version to survive. Reality is stranger than the version your senses give you. The strangest thing about reality is not that it hides from you, but that it reaches you only after being translated into a private language your brain can understand. You open your eyes and feel as if the world simply appears. The room, the walls, the distance between objects, the quiet shape of your own hands resting in front of you. It feels direct, immediate, almost obvious. But what you call the world is not arriving inside you whole. It is not entering your mind like a finished picture. It is being sampled, filtered, compressed, and rebuilt from tiny fragments of information. And your senses are not windows in the simple way we like to imagine. They are more like narrow instruments, each tuned to a small range of what exists, each ignoring far more than it receives. Your eyes respond only to a thin slice of electromagnetic radiation. Beyond that slice are waves your body does not turn into vision. Infrared warmth, ultraviolet patterns, radio waves passing invisibly through the space around you. Your ears catch only a certain band of vibration, while lower and higher frequencies continue moving through the air without becoming part of your ordinary awareness. Your nose, skin, and tongue also work within limits, not because reality is small, but because your body is selective. It gives you not the full universe, but the version useful enough to keep you alive. And that is the first quiet shock. Perception is not designed to show you everything. It is designed to show you what matters for a creature like you, moving through the world with a human body, human needs, human dangers, and human habits. A bee, a bat, a snake, a dog, and a human being can occupy the same place and yet live inside very different sensory worlds. The bee can respond to ultraviolet patterns in flowers that your eyes simply do not reveal. A bat can navigate with echoes so precise they turn sound into a kind of map. A snake can sense heat in ways that make warm bodies stand out from the background. A dog can read a street through scent with a richness that would feel almost supernatural if you could experience it for 1 minute. None of these animals is living in a fantasy. They are touching real features of the same world, but through different doors. This means your reality is not false exactly. It is limited. It is edited. It is one possible interface with something larger than the mind can hold all at once. And when you understand this, the ordinary world begins to loosen. A plain room is no longer plain. It is full of information you cannot detect. Faint heat patterns, chemical traces, microscopic movements, electromagnetic signals, air currents, vibrations, and histories written into surfaces too subtly for your senses to read. You are not surrounded by emptiness. You are surrounded by unread messages. Your brain protects you from the overwhelm by simplifying. It takes the storm of incoming signals and turns it into a stable scene, a manageable world, a place where a chair is just a chair and a shadow is just a shadow. That simplification is useful. Without it, life would be impossible. You could not walk, speak, choose, or rest if every hidden layer of reality came flooding into consciousness at once. But usefulness is not the same as completeness. A map can guide you through a city while leaving out the smell of rain, the sound of footsteps, the age of every stone, the lives behind every window. In the same way, your senses guide you through reality by leaving almost everything out. This is not a failure of the body. It is the price of being embodied at all. To be a living creature is to receive the universe through a specific shape. Your hands, eyes, ears, and nervous system are not neutral observers. They are the conditions under which reality becomes experience. And that is why certainty can be so fragile. You may feel that what you perceive is simply what is there, but another creature standing beside you would disagree without lying. Its world would be built from signals you miss, and yours would be built from signals it may not care about. Even among humans, attention changes the version of reality that becomes available. When you are afraid, the world sharpens around possible threats. When you are calm, details soften and widen. When you are searching for something, your awareness highlights what fits the search and lets other things fade. The outside world does not disappear, but your access to it changes. You are always meeting reality through a living filter. And perhaps the deepest lesson is not that you should distrust your senses completely, but that you should hold them with humility. They are miraculous, but they are not total. They let you cross streets, recognize faces, taste fruit, hear music, and feel the warmth of another person nearby. They give you a world rich enough to love, fear, explore, and remember. But they do not give you the whole. They give you a human edition of the real. So the next time you look around and feel that everything is obvious, pause for a moment. The quiet room around you is not as simple as it seems. The air is carrying things you do not hear. The light is holding patterns you do not see. The surfaces around you are alive with textures and traces your body reduces into something manageable. Reality is not smaller than your senses. It is larger. And you are not trapped because you cannot perceive all of it. You are invited to wonder because you can perceive just enough to know there is more. You live slightly behind the real world. By the time the world reaches you, it has already moved on. You do not experience life exactly as it happens, even though it feels that way with almost perfect confidence. A hand waves, a car passes, a face changes expression, a bird lifts from a branch, and your mind tells you, I am seeing this now. But the word now is softer, stranger, and less immediate than it feels. Light has to enter your eyes. Signals have to travel through the optic nerve. The brain has to sort edges, motion, depth, brightness, and meaning. Sound has to vibrate the eardrum, move tiny bones, ripple through fluid in the inner ear, and become nerve impulses before it can be understood as a voice, a footstep, or a door closing. Touch has to travel from the skin through nerves and into the spinal cord and brain before it becomes pressure, warmth, pain, or texture. None of this takes long in everyday terms. We are usually speaking about tiny slices of time, often measured in milliseconds. But tiny is not the same as zero. Your awareness is always arriving just after the physical event. You are not standing at the front edge of reality. You are living in a carefully stitched echo of it, close enough to feel immediate, delayed enough that the brain must constantly guess what is happening before the evidence is fully complete. This is the quiet miracle that lets you function. If your brain waited passively for every signal to arrive and be fully processed, you would be too slow for a moving world. You would reach for objects too late, dodge danger too late, catch a ball too late, understand speech too late. So instead, your brain predicts. It does not merely report the present. It estimates the present. It uses what just happened to prepare for what is probably happening now. When something moves across your vision, your brain does not treat each moment like a separate photograph. It builds a flowing expectation, a small forecast. So the moving object appears where it is likely to be, rather than where the old signal first began. This is one reason motion feels smooth instead of broken into delayed fragments. Your mind is not simply receiving the world, it is leaning forward into it. One famous clue comes from visual illusions like the flash lag effect, where a moving object and a flash that occur in the same moment can appear slightly misaligned. The moving object may seem ahead of the flash, not because the object broke the rules of time, but because your brain handles motion and sudden events differently. Motion gives the brain a pattern to predict. A flash arrives with no warning. The result is a strange little crack in the feeling of now, revealing that your perception is assembled from processes that do not all arrive at consciousness together. Even your body participates in this hidden delay. Touch your own finger to your other hand, and the sensation feels immediate, unified, almost impossible to separate into cause and effect. Yet the command to move and the feeling of contact are processed through different pathways. Your brain has to coordinate action and sensation so that the world does not feel like a badly synced film. It also dampens some of the sensations caused by your own movements, which is one reason you usually cannot tickle yourself the same way another person can. Your brain predicts the consequences of your own action, and because it expected the touch, the surprise is reduced. This means the feeling of being present in your body is not raw reality. It is a timing achievement. It is the brain keeping movement, sensation, and intention aligned closely enough that you feel like one continuous self moving through one continuous world. And this delay is not only visual or physical. Speech also lives inside timing. When someone speaks to you, your brain begins predicting the next sounds and even the next words before the sentence is finished. That is why you can understand fast conversation, why you can sometimes complete someone's sentence, and why a pause in the wrong place can feel uncomfortable. Listening is not waiting. Listening is active anticipation. Your brain is always trying to arrive at meaning before the sound has fully unfolded. This is beautiful, but it also means your experience of the present is partly made from expectation. You are always standing on a bridge between what has just happened and what your brain believes is about to happen. Most of the time, the bridge holds. The prediction is good enough, the delay is hidden, and life feels seamless. But when something surprising happens, you can feel the system strain. A sudden loud sound makes you flinch before you fully understand it. A near accident can make time feel stretched, not because external time truly slows down, but because attention and memory become unusually dense. In frightening moments, the brain may record more detail, and your later memory may make the event feel longer than it was. The present you lived and the present you remember are not always identical. Still, the key truth remains simple and unsettling. The now you trust is not a perfect point. It is a small construction zone, a living delay, a prediction wrapped around late arriving signals. And maybe this should make you gentler with your own certainty. You are not a machine reading the universe instantly. You are a nervous system trying to keep up with a reality that never stops moving. Every moment you experience has already passed through a hidden process before it becomes yours. The smile you notice, the music you hear, the step you take, the sentence you understand, all of it reaches awareness after the world has already turned slightly ahead. Yet this does not make life less real. It makes it more astonishing, because somehow, from delayed signals and constant predictions, your brain gives you the feeling of being here. Not perfectly on time, but close enough to love the world, respond to it, survive inside it, and wonder about it. You live slightly behind the real world, yes, but you also live inside one of nature's most delicate illusions. The feeling that you are meeting the present face to face, while your mind is quietly running after it, catching up just in time to call it now. Your memories change every time you recall them. Your past is not stored inside you like a finished film waiting to be replayed. It is rebuilt each time you return to it, and every act of remembering can quietly change the memory itself. This feels almost impossible at first, because some memories seem solid enough to stand on. You may remember the layout of an old room, the sound of someone's voice, the exact feeling of a sentence that hurt you, the weather on a day that mattered, the color of a shirt, the look on a face, the small details that make the past feel sealed and untouchable. But the brain does not preserve most experiences like a camera preserves footage. It stores pieces, sights, emotions, meanings, body sensations, fragments of language, clues about where you were, and the general shape of what happened. Later, when you remember, your brain gathers those pieces and rebuilds the event into a story that feels complete. The strange part is that the rebuilding process is not perfectly neutral. Each time a memory is brought back into awareness, it can become flexible for a short time, open to being updated by your current emotions, beliefs, knowledge, and the way the memory is being recalled. Scientists often call this process reconsolidation. After a memory is reactivated, the brain has to stabilize it again, and during that window, new information can become woven into the old trace. This does not mean every memory becomes false the moment you think about it, and it does not mean the past is imaginary. It means memory is alive. It is not a stone tablet. It is more like wet clay that hardens, softens when touched, and hardens again with the fingerprints of the present pressed into it. This is why two people can share the same event and later remember it differently. Not simply because one person is dishonest, but because attention, emotion, and meaning shape what gets stored and what gets restored. Your brain tends to remember what mattered to you, not everything that happened. A frightening moment may preserve the feeling of danger while losing ordinary details around it. A joyful moment may keep the warmth and blur the exact sequence. An embarrassing moment may grow sharper in shame than it ever was in reality. And over time, your mind may fill gaps with details that seem reasonable, because the brain prefers a coherent story to a broken collection of fragments. This is one reason eyewitness memory can be surprisingly unreliable. A person can be sincere, confident, and still mistaken. Confidence is not a perfect measure of accuracy. It is often a measure of how familiar or emotionally strong the memory feels. Experiments in psychology have shown that suggestion can influence what people later believe they remember. A leading question, a repeated story from someone else, a photograph seen later, or even hearing family members describe an event can sometimes add details that were not part of the original experience. The mind may adopt them because they fit the story. Slowly, the borrowed detail begins to feel self-generated. This is not weakness. It is how a storytelling brain tries to maintain continuity. Your memory system was not built mainly to archive the past with perfect precision. It was built to help you survive the future, remembering where danger happened, who comforted you, what choices led to pain, what paths led home, what patterns repeated. These are useful. The brain keeps the past not as a museum, but as a guidebook, and guidebooks are edited for usefulness. They highlight meaning, they simplify, they connect old events to new decisions. That is why a memory can change after you understand something differently. A childhood moment that once felt confusing may later feel sad when you understand the adult world around it. A failure that once felt humiliating may later become proof that you endured. A goodbye that once felt like abandonment may soften when you learn what the other person was carrying. The facts may not change, but the memory's emotional shape can, and because emotion is part of memory, the remembered past itself feels different. This is where the science becomes deeply human. Healing often involves returning to memories in safer conditions, with new support, new language, and a wider understanding. The goal is not to pretend the past did not happen. It is to let the brain update the meaning around it. A painful memory can remain painful, but it may no longer have to feel like a living threat. It can become something that happened to you, rather than something that is still happening inside you. But the same flexibility can also trap you if you revisit a memory in the same fear again and again. Each replay can strengthen the path, deepen the emotional groove, and make the story feel even more final. This is why the way you remember matters. The questions you ask matter. Why was I so stupid? Builds one kind of memory. What did I not know yet? Builds another. Why did this ruin me? And how did I survive this? May look at the same past, but they do not return you to the same self. Memory is not only recall, it is relationship. You are always in relationship with your former life, always touching it from the present moment, always letting today's mind speak to yesterday's pain, joy, confusion, or wonder. And perhaps the most unsettling part is also the most merciful. You do not have perfect access to who you were, but you are not completely imprisoned by one version of what happened. The past leaves marks, but the meaning of those marks can move. So when you remember something tonight, when an old scene rises without warning, try to notice the quiet act taking place. Your brain is not opening a vault. It is rebuilding a room. Some objects may be exactly where they were. Some may have shifted. Some may have been added by fear, by longing, by repetition, by stories told afterward. Walk gently there. Do not assume every detail is a lie, but do not worship every detail as truth. Memory is one of the brain's most beautiful compromises. Fragile enough to change, strong enough to shape a life. And every time you recall who you were, you are not only visiting the past, you are helping decide what that past will mean when it returns with you into tomorrow. The world has no color until your brain creates it. A red apple is not actually red in the way it seems to be red. It is holding back most of the light that falls on it, reflecting a certain range back toward your eyes, and then your brain turns that returning light into the private experience you call color. That may sound like a small correction, but it quietly changes the entire room you are sitting in. The blanket, the screen, the skin of your hand, the blue of the sky, the green of leaves, the warm gold of evening sunlight. None of these colors are painted onto the outside world in the simple way they feel. Out there, beyond your skull, there is light of different wavelengths, surfaces absorbing and reflecting parts of that light, and eyes collecting the result. The color itself appears only when the nervous system interprets the signal. In that sense, color is not a property sitting alone inside an object. It is a relationship between light, matter, eyes, and brain. Change any part of that relationship, and the color can change too. A shirt that looks black under one lamp may look slightly blue under another. A wall that seems white at noon may glow orange at sunset. A fruit that looks ripe to you may appear different to an animal with a different visual system. The world is not colorless in the sense of being empty or dead. It is full of physical information, but the redness, blueness, greenness, and brightness that feel so immediate are experiences created by the brain from that information. Your eyes begin this process with special cells in the retina called cones. Most people have 3 main types of cones, each more sensitive to a different range of light. They do not work like tiny paint detectors labeled red, green, and blue in a simple way. Instead, they respond in overlapping patterns, and your brain compares those patterns to build a sense of color. Color is made through contrast, comparison, and interpretation. This is why the same patch of gray can look lighter or darker depending on what surrounds it. Place it beside black, and it may seem brighter. Place it beside white and it may seem darker. The patch itself has not changed, but your brain's judgment of it has. It is also why after images happen. Stare at a strong color for a while, then look at a blank surface, and you may see its opposite appear faintly, like a ghost left behind by tired visual pathways. Your brain is not simply recording color. It is balancing color, correcting it, predicting it, and sometimes overcorrecting it. One of the most useful tricks it performs is called color constancy. Imagine a banana under morning light, under cloudy light, and under warm indoor light. The actual light reaching your eyes changes in each situation, but you still tend to see the banana as yellow. Your brain estimates the lighting conditions and tries to subtract the color of the light source so the object remains stable. Without this ability, the world would feel wildly unstable every time you moved from shade to sun. You would have trouble recognizing food, faces, clothes, and objects because their appearance would shift too dramatically with every change in illumination. So the brain makes a practical compromise. It does not show you raw light exactly as it arrives. It shows you a corrected version that helps objects remain recognizable. Most of the time, this works beautifully, but sometimes it produces disagreements so strong that 2 people looking at the same image may insist on different colors. The famous dress illusion became popular because some people saw a dress as blue and black, while others saw it as white and gold. The image itself was ambiguous because the lighting was unclear. Different brains made different assumptions about whether the dress was in shadow or bright light, and those assumptions changed the perceived colors. This is not proof that people can choose colors however they want. It is proof that color perception depends on hidden judgments your brain makes before you're aware of them. And this should make the familiar world feel a little more delicate. Color feels like one of the most solid parts of reality, yet it is deeply dependent on context. Painters, photographers, filmmakers, and designers use this constantly. A color can feel warmer beside a cool background, more intense beside its opposite, softer in dim light, sharper in contrast. The emotional power of color also comes from the brain's associations. Red can signal fruit, blood warning, warmth, danger, or love depending on context. Blue can feel calm, cold, distant, clean, or sad. The physical light matters, but the meaning is built by a living mind. Even colorblindness reveals how constructed color is. Someone with a different cone response may not separate certain reds and greens the way another person does. Yet they are not seeing wrong in a moral sense. They are living with a different color map. Their world is organized by a different set of comparisons. And some people, very rarely, may have variations in color vision that let them distinguish shades others cannot easily separate. Color is not one universal window shared identically by every human. It is a biological negotiation. The universe offers light. The eye samples it. The brain composes experience from it. So when you look at the world and call it colorful, you are witnessing both nature and yourself. The flower is not lying. The sky is not fake. The apple is not pretending. But the color you feel blooming from them is something your brain participates in making. This does not make beauty less real. It may make beauty more intimate, because every color you have ever loved, the pale blue of early morning, the deep green after rain, the orange line of sunset at the edge of the horizon, has existed not only outside you, but also through you. The world gives the signal, but your mind lights the lantern. And perhaps that is why color feels so emotional. It is where physics becomes sensation, where invisible waves become memory, where the outside world touches the nervous system and returns as wonder. The next time you see a red apple, do not think of it as less real because the redness is created in your brain. Think of it as a meeting place. Light has traveled, the surface has answered, your eyes have listened, and your brain has turned that exchange into color. Reality did not arrive already painted. You helped paint it by being alive. You are mostly empty space, but can't walk through walls. The wall in front of you is not solid because it is completely full. It is solid because the emptiness inside it refuses to let your emptiness pass through. At first, this sounds like a trick, because your hand feels dense, the table feels firm, the floor holds your weight, and the world seems built from hard, continuous stuff. But when you move down into the hidden architecture of matter, the familiar picture breaks open. Every object around you is made of atoms, and an atom is not like a tiny marble packed tightly beside other marbles. It is more like a small center of mass, surrounded by a wide region of probability and energy. The nucleus at the center contains almost all the atom's mass, but it is incredibly small compared with the space around it. If an atom were expanded to the size of a stadium, the nucleus would be more like something tiny near the center, while the rest would be an enormous region where the electrons are not orbiting like little planets in neat circles, but existing as spread out quantum patterns. So, when people say you are mostly empty space, they are pointing to a real and astonishing fact. The matter that makes your body is not packed edge to edge with solid material. The atoms in your skin, bones, blood, and brain contain vast internal gaps compared with the size of their nuclei. The same is true of the wall, the chair, the ground, the glass in a window, and the metal in a door handle. Almost everything you touch is made from structures that are mostly not stuff in the everyday sense. And yet you cannot walk through walls. You cannot push your hand through a table. You cannot step through a closed door by reminding yourself that atoms contain empty regions. Why? Because emptiness at the atomic level is not the same as open space at your level. It is not a hallway waiting to be used. It is filled with fields, forces, and quantum rules that decide how matter behaves. When your hand presses against a wall, the atoms in your skin approach the atoms in the wall, and the outer electrons of those atoms begin to interact. Electrons have electric charge, and like charges resist being pushed too close together. This electromagnetic interaction is one of the main reasons surfaces feel solid. You are not really touching the wall in the way your senses imagine, with two pieces of matter merging at their edges. What you feel as contact is the resistance between the charged particles in your hand and the charged particles in the wall. Your nerves translate that resistance into pressure. Your brain calls it touch. The wall says no long before your atoms could simply slide into its atoms. But there is an even deeper rule at work, one that makes ordinary matter stable instead of collapsing into itself. It is called the Pauli exclusion principle, and in simple terms, it says that certain particles, including electrons, cannot all occupy the exact same quantum state at the same time. This rule is not a polite suggestion. It is part of the structure of nature. It helps explain why atoms take up space, why electrons arrange themselves in shells and patterns, why chemistry has structure, why matter does not all fall into one dense blur, and why your body has form. Without this principle, the world would not merely be softer. It would be unrecognizable. The architecture of atoms, the strength of materials, the shapes of molecules, even the stability of your own body depend on quantum rules that prevent matter from being compressed without limit. So, the wall is mostly empty, only if you imagine matter as tiny hard balls separated by nothing. But that image is too simple. The empty part of an atom is not meaningless emptiness. It is where electron clouds exist, where electric fields extend, where quantum behavior gives matter its size and structure. The reason your body cannot pass through the wall is not because every microscopic gap is physically blocked by little solid beads. It is because the patterns that make up your atoms and the patterns that make up the wall cannot simply overlap freely. They push back. They reorganize. They resist. At your scale, all those microscopic refusals combine into one simple experience: hardness. This is why a wooden table can hold a cup, why a steel beam can support a building, why your feet do not sink through the floor, and why a hug has warmth and pressure instead of two bodies passing silently through each other like ghosts. There is a strange beauty in this. Solidity is not what it seems. It is not the absence of space. It is the presence of rules. It is nature creating boundaries from invisible interactions. And yes, quantum physics does allow something called tunneling, where tiny particles can sometimes pass through barriers they would not have enough energy to cross in ordinary physics. This is real and important. It helps explain processes in the sun and certain technologies on Earth. But for something as large as you, made of an enormous number of particles all arranged together, the chance of every part of your body tunneling through a wall in a coordinated way is so unimaginably small that it is not a practical possibility. You are not prevented from walking through walls because the universe lacks imagination. You are prevented because your body is a vast organized system, and the wall is another vast organized system, and the quantum rules that govern them do not casually allow one to pass through the other while remaining intact. This also means that the feeling of solidity is a kind of large-scale agreement. Atoms do not feel solid individually in the way a stone feels solid in your palm. But when countless atoms interact together, their forces become structure, their resistance becomes surface, their arrangement becomes wood, bone, glass, skin, stone. The ordinary world rises from invisible negotiations happening everywhere, constantly, faster and more quietly than thought. You lean against a wall and feel support, but beneath that simple moment is an entire civilization of particles maintaining distance, obeying rules, exchanging forces, refusing collapse. You are mostly empty space, but you are not insubstantial. You are not a loose cloud pretending to be a person. The emptiness inside you is organized by energy, held together by fields, shaped by quantum principles, and stabilized by interactions so dependable that life can stand upright and call the ground solid. And maybe that is the most humbling part. What feels most certain in your life? The floor beneath you, the chair under your body, the cup in your hand, is built from something far stranger than certainty. It is built from tiny centers of mass surrounded by vast regions of possibility, from invisible forces that never sleep, from rules that turn emptiness into resistance and resistance into form. So the next time your hand touches a wall, pause for a second. You are not meeting a simple barrier. You are meeting the hidden structure of matter itself. You are feeling electrons push back, quantum rules hold their ground, and emptiness becomes solid enough to stop you. The wall is not full in the way it appears to be. Neither are you, and yet, here you both are. Two mostly empty things unable to pass through each other, because the universe has learned how to make emptiness feel like stone. Your eyes see less than your brain pretends. Your eyes give you only a small island of sharpness, and your brain quietly convinces you that the whole world is clear. Look around the room for a moment, and it feels as if everything is equally visible. The edge of a table, the corner of a wall, the pattern on a distant object, the movement near the side of your vision, the words on a screen, the shape of your own hands. It feels like your eyes are taking in the full scene at once, like a wide camera capturing reality in crisp detail from edge to edge. But that feeling is one of the brain's most elegant illusions. In truth, the part of your vision that is sharply detailed is extremely small. At the center of your retina is a tiny area called the fovea, packed with cone cells that allow you to see fine detail and read small text. This is the part you are using when you look directly at a word, a face, a thread, a star, or the tip of a pencil. But outside that central point, visual detail drops quickly. Your peripheral vision is very useful, but it is not sharp in the same way. It is better at noticing motion, broad shapes, changes in light, and possible danger. It is not built to read a sentence at the edge of your vision, or inspect the fine lines of a face without turning your eyes toward it. Yet you rarely notice this loss of detail, because your brain does not present your visual world as a small sharp center surrounded by a blurry field. It gives you the feeling of a complete, stable, detailed world. This is partly because your eyes are constantly moving. Even when you think you are calmly staring, your eyes make rapid movements called saccades, jumping from point to point several times a second. Each jump brings a different part of the scene onto the fovea, gathering high-quality samples from the world. Your brain then uses these samples, along with memory, expectation, and general knowledge of the scene, to create the impression that you are seeing everything clearly at once. But you are not. You are sampling. You are scanning. You are receiving fragments, and the brain is turning those fragments into a confident whole. This is why you can miss huge changes right in front of you when your attention is elsewhere. In experiments on change blindness, people can fail to notice major differences between two images, or even miss an unexpected object in a scene, especially when their attention is focused on a task. The eyes may technically receive the light, but receiving light is not the same as consciously seeing. Vision is not just what enters the eye, it is what the brain selects, organizes, and decides is worth bringing into awareness. This matters because we often treat seeing as proof. We say, "I saw it with my own eyes," as if that ends the question. But your eyes do not operate like neutral recording devices. They have limits. They move, they skip, they prioritize. They send the brain an enormous flow of information, and the brain must choose what to emphasize and what to ignore. Your visual system is not trying to give you a perfect copy of the world. It is trying to give you a useful version fast enough for action. If something moves suddenly at the edge of your vision, your eyes may snap toward it before you even understand why. If a face appears in a crowd, your attention may lock onto it, because faces are socially important. If you are looking for your phone on a messy table, objects that resemble its shape or color may stand out while unrelated details fade. Your brain is always asking, what matters here? What might be dangerous? What am I searching for? What do I already expect this scene to contain? That is why two people can look at the same place and notice entirely different things. A mechanic sees engine problems where someone else sees only metal. A doctor may notice a subtle sign on a scan that an untrained eye would miss. A painter may see shadows and proportions that others pass over. Their eyes are not necessarily receiving a different world. Their brains are trained to pull different meaning from it. Vision is learned as much as it is received. Even reading depends on this hidden efficiency. You do not examine every letter with equal attention. Your brain recognizes word shapes, uses context, predicts what comes next, and often corrects small errors without asking your permission. This is why you can sometimes read a sentence with missing or mixed letters, as long as the overall structure remains familiar. The brain is not waiting for perfect input. It is making intelligent guesses. Most of the time, those guesses are helpful. They let you move through a complicated world without drowning in detail. But they also mean that what you experience as clear sight is partly a construction of attention. You see sharply where you look, vaguely where you do not, and confidently where your brain believes it already understands enough. There is something humbling in this. The world you feel you are seeing all at once is actually being assembled through glances, priorities, and assumptions. Your eyes are narrower than your experience suggests, but your brain is generous. It expands a small point of clarity into a wide sense of presence. It lets you feel surrounded by a complete world, even though your sharp vision is always moving like a lantern beam in a dark field. And maybe this should make you slower to trust the feeling that you noticed everything. Maybe it should make you more patient with others, more careful with memory, more curious about what your attention leaves behind. Because every moment, the visible world contains more than you consciously take in. Your eyes are not lying to you, but they are not telling the whole story either. They are offering pieces, and your brain is quietly turning those pieces into a world. So the next time you look across a room and feel certain that you see it all, remember the small island of sharpness inside your gaze. Remember the quick jumps your eyes make, the details your attention selects, the blur your brain politely hides from you. You do not see as much as you think, but from that limited stream, your mind builds a place you can live in, move through, and love. And perhaps that is the quiet wonder of vision. Not that it shows you everything, but that it shows you just enough to make the world feel whole. You never hear pure silence. Your brain adds noise. Silence is not an empty room in the mind. It is a quiet stage where your brain begins to reveal the sounds it usually hides. You may think silence means the complete absence of sound, a clean blankness where nothing vibrates, nothing reaches the ear, and nothing is heard. But in real life, almost no silence is truly pure. Even when a room feels still, there may be distant air movement, the faint hum of electricity, the soft pressure of your own breathing, tiny shifts in furniture, blood moving through vessels near the ear, joints settling, fabric brushing skin, or the low background murmur of the world beyond the walls. Your ears are sensitive instruments, built not only to detect obvious sounds, but to keep listening even when nothing important seems to be happening. And when outside sound becomes very low, something strange begins. Your attention turns inward. The quieter the world gets, the more your own body and nervous system become audible. This is why people inside extremely quiet spaces, such as anechoic chambers, designed to absorb echoes and outside noise, often report hearing sounds they normally ignore. Their heartbeat, their breath, faint ringing, pulsing, or the subtle internal rustle of being alive. The chamber is not creating those sounds. It is removing the ordinary noise that usually covers them. Silence does not always give you nothing. Sometimes it gives you yourself, amplified. But the story goes deeper than body noise. Your auditory system is never completely off. The brain is an active organ, not a passive microphone waiting for the world to press play. Nerve cells have spontaneous activity. Circuits maintain a background level of signaling. Your hearing system is constantly adjusting sensitivity, filtering patterns, and preparing to detect meaningful changes. In a dangerous world, a nervous system that stopped listening during quiet would be a poor guardian. So the brain keeps a kind of watchful readiness. It asks, even in stillness, is that a threat, a voice, a movement, a signal, a pattern? This readiness can make silence feel textured rather than empty. If you lie awake at night in a dark room, you may notice faint tones, a soft hiss, a distant ringing, or a pressure-like sound that seems to come from nowhere. For many people, these sensations are brief and harmless, a normal part of a listening system turned toward itself. For others, especially those with tinnitus, the internal sound can become persistent and intrusive, often experienced as ringing, buzzing, hissing, or tones without an external source. Tinnitus can have many causes, including hearing damage, age-related changes, ear conditions, certain medications, stress, or changes in how the brain responds after reduced input from the ear. One useful way to imagine it is this. When the brain receives less clear sound from certain parts of the hearing system, it may increase its internal gain, like turning up the volume on a quiet radio station. But when you turn up the volume too far, you may also hear static. That static is not imaginary. It is a real perception generated by the nervous system, even if it does not come from an outside object. This teaches us something important about hearing. Sound, as you experience it, is not merely vibration in the air. Vibration is the beginning. Hearing is the brain's interpretation of that vibration, and sometimes the brain can produce an auditory experience even when the outside vibration is missing or unclear. This is not unique to hearing. The nervous system often fills, sharpens, predicts, and stabilizes experience. But silence makes the process easier to notice because it removes the usual cover. It is like turning off the lights in a city and suddenly seeing the stars. The stars were there before, but the brighter noise hid them. In the same way, the brain's inner noise is often masked by traffic, voices, music, wind, machines, footsteps, and the endless small sounds of daily life. When those fade, the hidden layer appears. This may also explain why complete quiet can feel peaceful to one person and unsettling to another. If your mind is calm, silence can become a soft container, a place where breathing slows and attention widens. But if you are anxious, silence may become too spacious. The brain may search harder for signals, and the absence of clear sound can feel like suspense. A floor creak becomes meaningful. A distant pipe becomes a possible footstep. A faint internal tone becomes difficult to ignore. The quiet does not simply arrive. It meets the state of the listener. Your brain does not hear silence as a neutral absence. It hears it through expectation, memory, alertness, fatigue, and emotion. That is why a silent house at noon and a silent house at midnight can feel like two different places. The physics may be similar, but the nervous system has changed the meaning. And perhaps this is the most fascinating part. Your brain is not built to worship silence as emptiness. It is built to notice contrast. A sound matters because it rises from a background. A whisper feels intimate because it is surrounded by quiet. Music moves you because notes appear and disappear, because pauses give shape to melody. Silence is not the opposite of sound in experience. It is part of how sound becomes meaningful. A song without silence would be a wall. Speech without pauses would be noise. Even rest depends on what is absent, so when you sit in silence, you are not entering nothing. You are entering the background against which your brain measures the world. You may hear your breath, your pulse, the faint electrical weather of your own hearing, or the soft imagined edge of sounds that are not there. None of this means silence is fake. It means silence is not as simple as it seems. It is not a perfect void waiting outside you. It is a relationship between the world's quietness and the brain's refusal to stop listening. So the next time everything around you grows still, do not rush to fill the space. Listen carefully but gently. Notice how the quiet has layers. Notice how your body becomes part of the room. Notice how the mind begins to add its own faint texture when the world stops speaking loudly. You may never hear pure silence, not because silence is impossible in theory, but because you are alive, and life is not silent from the inside. Your brain keeps a small lantern burning in the dark, listening for meaning, adding signal, holding watch. And in that faint inner noise, there is something deeply human. Proof that even when the world goes quiet, your mind is still reaching outward, still trying to understand, still turning emptiness into experience. your sense of touch is mostly electrical repulsion. When your fingertips meet a piece of glass, a wooden table, or another human hand, the most intimate part of the experience is not matter merging with matter, but invisible charged particles refusing to let each other overlap. Touch feels like direct contact, like your skin has reached the final edge of the outside world and pressed against it. A cold cup, a soft blanket, a rough stone, a warm shoulder. Each one seems to arrive as a simple fact through the skin, but beneath that familiar feeling is a hidden chain of events. And the first surprise is that touch is not as straightforward as skin-touching object. At the deepest physical level, the outer parts of atoms are made of electrons, and electrons carry negative charge. When the electrons in your skin come close to the electrons in another surface, they resist being pushed into the same space. That resistance is part of what gives contact its firmness. You do not need to sink into an object to feel it. The repulsion begins at unimaginably tiny distances, and your body turns that resistance into pressure, texture, weight, and shape. This means every touch is partly a negotiation between electric charges. The world pushes back before your body can pass into it. But the story does not stop at physics, because the feeling of touch only begins there. The resistance between surfaces bends and stretches your skin by tiny amounts. And inside your skin are specialized nerve endings waiting for those changes. Some respond to steady pressure, helping you know that a coin is resting in your palm. Some respond to light fluttering, helping you feel a sleeve brush against your arm. Some respond to vibration, which is why you can sense the buzz of a phone or the fine texture of a surface as your finger moves across it. Others help detect skin stretch, telling your brain how your hand is gripping, pulling, or shaping itself around an object. These receptors do not send the brain a picture of the object itself. They send electrical signals about deformation, movement, pressure, vibration, temperature, and sometimes damage. Your brain then builds the experience you call touch. So when you close your eyes and recognize a key in your pocket, you are not reading the key directly. Your fingers are gathering clues. Hard edges, grooves, weight, coolness, the way metal slides against skin. Your nervous system assembles those clues into recognition. This is why touch is not just a passive sense. It is active exploration. You move your fingers to know. You press, stroke, squeeze, tap, lift, and adjust. A surface that feels smooth when your finger rests still may reveal hidden texture when you slide across it, because motion creates patterns of friction and vibration that receptors can detect. Fine textures may be felt not because each tiny ridge is consciously measured, but because movement turns surface detail into a tiny song of vibration traveling through the skin. Your fingertips are especially sensitive because they contain a dense population of touch receptors and occupy a large amount of space in the brain's sensory map. The brain gives your hands special importance because they are how you investigate the world, feed yourself, protect yourself, build tools, comfort others, and learn the shape of things in the dark. In a very real sense, your hand is not only a body part, it is an instrument of understanding. And yet the feeling of contact remains strangely indirect. The pressure begins with physical resistance, becomes mechanical change in the skin, becomes electrical activity in nerves, travels through the spinal cord, passes through processing centers, and finally becomes an experience in awareness. By the time you say, "This is soft" or "This is sharp," your brain has already performed a quiet translation. Softness is not a single property floating inside the object. It depends on how much the surface yields, how quickly it deforms, how warm it is, how it moves against your skin, and what your brain expects. A sponge, a feather, and human skin can all be called soft, but each creates softness in a different way. Roughness also depends on scale and movement. A surface may feel smooth to the palm but rough to the fingertip. A texture may feel different if you move slowly or quickly. Even wetness is more complicated than it seems, because humans do not have a simple wetness receptor, the way we have receptors for temperature and pressure. Your brain often infers wetness from a combination of cooling, slipperiness, pressure changes, and context. That is why something cold and smooth can sometimes feel damp even when it is dry. Touch is the brain making sense of a conversation between skin and world. This also explains why touch can be emotional so quickly. Physical contact is not only information, it is safety, boundary, threat, care, and memory. A gentle touch can slow the body. A painful touch can teach caution. A sudden touch can trigger alarm before you have time to think. The same pressure on the skin can feel comforting or invasive depending on who gives it, when it happens, and whether you expected it. Your brain does not separate touch from meaning. It asks not only what is pressing against me, but is this safe, wanted, dangerous, familiar, alive? That is why a handshake, a hug, a hand on the shoulder, or the texture of an old object can carry more than physical sensation. Touch is where physics becomes biology, and biology becomes feeling. It begins with charged particles pushing back, but it ends as trust, discomfort, recognition, warmth, or memory. And perhaps that is the quiet wonder hidden in every ordinary contact. You never truly pass into the world, and the world never truly passes into you. Yet from that tiny refusal, your life becomes tangible. A surface resists, your skin bends, nerves fire, the brain listens, and suddenly there is reality at your fingertips. So the next time you touch a table, a stone, a page, or someone's hand, pause for a moment. What feels simple is a layered event. Electric repulsion becoming pressure, pressure becoming signal, signal becoming perception, perception becoming meaning. You are not merely touching matter, you are feeling the boundary where your body and the universe politely refuse to become the same thing. And somehow, from that refusal, closeness is born. Your brain edits reality before you notice. Before you become aware of a moment, your brain has already cleaned it, trimmed it, corrected it, and handed you the edited version as if it were raw reality. You do not experience the world like an untouched recording. You experience a finished scene. A face appears stable as it turns. A room feels continuous as you move through it. Your own body seems to remain in one smooth flow from second to second. But underneath that calm surface, the brain is constantly working like an invisible editor, removing blur, filling gaps, reducing confusion, correcting errors, and deciding what should be allowed into consciousness. This editing begins so early that you usually mistake the final product for the original. You do not notice the cut. You only see the movie. One of the clearest examples happens every time your eyes jump. Your eyes do not glide smoothly across the world in the way your experience suggests. They make quick movements from one point to another. During these tiny jumps, the image hitting your retina would be messy and blurred if your brain showed it to you honestly. But instead of letting you experience the world as a shaky smear, the brain suppresses much of that unstable input and gives you a steadier visual scene. You feel as if you have been watching continuously, but your nervous system has quietly hidden the rough transitions. It is like walking through a hallway while someone turns the lights off and on between steps. Yet your mind presents the hallway as if it were evenly lit the entire time. This is not deception for its own sake. It is protection. A brain that showed every flicker, gap, and conflict in the sensory stream would leave you overwhelmed and slow. So it edits for usefulness. It gives you a world stable enough to act in. And this stability is one of the great achievements of perception. Think about what happens when you turn your head. The whole image on your eyes shifts. Yet the room does not feel like it is sliding wildly around you. Your brain uses signals from your muscles, your inner ear, and your intended movements to separate what changed, because the world moved from what changed, because you moved. If you turn your head left, the scene sweeps across your eyes, but you do not conclude that the walls flew right. The brain corrects for your own motion before the experience reaches awareness. This is why the world feels anchored even while your body is constantly adjusting. Your inner ear, especially the vestibular system, helps by detecting head movement and balance. It works with vision and body signals to keep your sense of space coherent. When those systems disagree, you may feel dizzy, nauseous, or unreal because the editor is receiving conflicting footage. Motion sickness is one familiar result. Your eyes may report one thing, your inner ear another, and the brain struggles to decide which version of reality to trust. The discomfort is not weakness. It is a sign that your reality-building system depends on agreement between senses. The brain also edits by filling in what it expects should be there. This does not mean it invents randomly. It uses context. If you hear a sentence in a noisy room and one sound is covered by a cough, you may still understand the missing part because your brain restores the likely word. In speech perception, the mind often uses surrounding sounds, language patterns, and meaning to complete what the ear did not clearly receive. You feel as if you heard the full sentence, but part of it was reconstructed. The same thing happens in everyday perception. The brain uses the surrounding pattern to make missing or unclear information feel complete. This is why a familiar song can still be recognized through bad speakers, why you can understand a friend in a crowded cafe, and why a half-hidden object can be identified from only a few clues. Your awareness is not waiting for perfect data. It is receiving an edited guess good enough to guide you. The danger is that the guess can feel just as real as the evidence. This is where perception becomes both powerful and fragile. In the brain, top-down expectations can shape bottom-up signals. What you expect, fear, desire, or are trained to notice can influence what stands out and what fades. A doctor may see a pattern in symptoms that others miss. A musician may hear a timing mistake that passes unnoticed by most listeners. A tired person walking alone at night may interpret an ordinary shadow as suspicious before realizing it is harmless. The brain is not only asking, "What is there?" It is also asking, "What is likely? What matters? What have I seen before? What should I prepare for?" That preparation happens quickly, often before conscious thought can correct it. This is why first impressions can feel immediate and convincing, even when they are incomplete. The brain has already made a quick draft of reality, and you meet the draft as if it were the final truth. Attention is another part of the editing process. The world contains too much information for full awareness, so the brain must prioritize. It sharpens some signals and dims others. When you focus on a task, background details may disappear from experience even though your senses are still receiving them. When your name is spoken across a room, it may suddenly rise out of the noise because it matters to you. The brain is not treating all information equally. It is ranking the world by relevance. This is why consciousness feels wide but is actually selective. You are not aware of everything your brain processes. Much of the work happens backstage. Posture adjustments, emotional appraisals, sound filtering, balance corrections, predictions about movement, tiny decisions about where attention should go next. By the time something becomes your experience, it has already passed through layers of selection. And yet, without this editing, reality would not feel more truthful. It would feel chaotic. The brain's edits are what let you cross a street, follow a conversation, recognize a friend from a glimpse, keep your balance, and feel that the world continues to exist from one moment to the next. The problem begins only when you forget that editing is happening. You may mistake your version for the only version. You may trust a fear because it appeared quickly. You may believe you saw everything because the scene felt complete. You may assume your first interpretation is reality itself, when it may only be the brain's fastest attempt to make sense of limited information. So the lesson is not to distrust your mind completely. The lesson is to respect how much work it is doing before you notice. Your brain is not a liar. It is a survival artist. It edits not to fool you, but to help you move through a world too rich, too fast, and too unstable to process without simplification. Still, awareness gives you a small freedom. You can pause before believing the first version. You can ask whether your fear added something, whether your expectation removed something, whether your attention missed something, whether the scene in your mind is a clean window or a careful edit. And in that pause, the world becomes deeper. Not less real, but more layered. Because every ordinary moment is not just happening to you, it is being shaped for you by a brain working silently in the dark, cutting the blur, smoothing the edges, choosing the signals, and handing you a reality you can survive inside. The next time everything feels obvious, remember this hidden editor. Before you notice the world, your brain had already touched it. Before you called it reality, your mind had already made it readable. Time runs differently, depending on gravity. The clock on your wrist is not keeping the same time everywhere in the universe. Lift it higher, place it near a mountain, send it into orbit, or carry it close to a black hole, and time itself begins to change its rhythm. This sounds like something invented for science fiction, because in daily life, time feels like the one thing that does not negotiate. A minute is a minute, an hour is an hour. Morning becomes afternoon, yesterday stays behind you, tomorrow waits ahead. But modern physics tells a stranger and more careful story. Time is not a single universal river flowing at the same speed for everyone. Time is woven together with space, and gravity changes the shape of that fabric. The stronger the gravity around you, the slower your time passes, compared with someone farther away from that gravity. This does not mean you would feel yourself slowing down. If you stood on the surface of Earth, your heartbeat would feel normal. Your thoughts would feel normal. Your watch would seem normal. Time always feels ordinary from inside your own frame of experience. The weirdness appears only when you compare your clock with another clock somewhere else. A clock closer to Earth's surface, where gravity is slightly stronger, ticks a tiny bit more slowly than a clock higher up, such as on a tall mountain or in a satellite. The difference is extremely small in human life, but it is real, measurable, and important enough that our technology must account for it. Atomic clocks, which are far more precise than ordinary clocks, have confirmed that clocks at different heights do not tick at exactly the same rate. Even raising a precise clock by a small height can change its ticking by a tiny amount. You do not notice it because your body is not sensitive to such small differences, but nature is. The universe keeps the receipt. One of the clearest everyday examples is GPS. The satellites above Earth carry clocks, and those clocks do not run exactly like clocks on the ground. Because the satellites are farther from Earth's mass, they feel weaker gravity, and that makes their clocks tick faster compared with clocks on Earth's surface. At the same time, because the satellites are moving quickly, another part of relativity makes their clocks tick slightly slower. Both effects matter, but the gravity effect is larger, so overall the satellite clocks run faster than ground clocks unless corrected. If engineers ignored this, GPS positions would drift and become inaccurate very quickly. So every time your phone finds your location, it is quietly using the fact that time changes with gravity. A strange truth about the universe is hiding inside ordinary navigation. You tap a map, and behind that simple blue dot is Einstein's idea that time is flexible. To understand why gravity affects time, it helps to stop imagining gravity only as a force pulling things downward. In Einstein's picture, mass and energy curve space-time, and objects follow paths through that curved structure. Earth does not just pull on you, it changes the geometry around you. A clock near a massive object moves through space-time differently from a clock far away. It is not broken. It is not delayed by a mechanical problem. It is experiencing time differently because the structure of reality around it is different. Near something incredibly dense like a black hole, this effect becomes extreme. Far from the black hole, an outside observer would see a clock near the edge appear to slow dramatically. Light escaping from that region loses energy, and events near the black hole seem stretched out from the distant point of view. But if you were falling inward, your own clock would not feel frozen to you. Your seconds would still feel like seconds. That is one of the most mind-bending parts of relativity. There is no single master clock above the universe telling everyone the true time. Time depends on where you are, how fast you are moving, and how gravity shapes the region around you. This does not make time unreal. It makes time local. It makes it intimate. It means the universe does not hand out one identical now to every place at once. The surface of Earth, the top of a tower, the orbit of a satellite, the edge of a neutron star, and the region near a black hole all have their own relationship with time. Even your head and your feet are, in an extremely tiny sense, living at slightly different rates because your feet are closer to Earth's center and therefore in slightly stronger gravity. The difference across your body is far too small to matter in ordinary experience, but the fact that it exists is astonishing. You are not just living in time, you are living inside a gradient of time, a gentle slope so subtle that your senses smooth it away. And this should change how you think about the word now. When you look up at the sky, you may imagine the universe sharing one vast present moment with you. But relativity suggests something more complex. Time is not a stage on which everything happens equally. It is part of the stage itself, bending with gravity, stretching with motion, changing from place to place. The stronger the gravity, the deeper the clock sits in spacetime's well, and the slower it ticks compared with clocks higher above. This is not a metaphor. It is one of the most tested ideas in physics. It helps explain the behavior of light, the motion of planets, the precision of satellites, and the strange environments around the densest objects in the cosmos. But beyond the science, there is something quietly humbling in it. You may feel that life is measured by the same seconds for everyone, but the universe is more personal than that. Time bends around worlds. Time thins and thickens around mass. Time is not simply passing over you like weather. It is shaped by the ground beneath you, the planet holding you, the stars around you, the invisible geometry that tells clocks how to breathe. So the next time you check the time, remember that the number you see is not the universal heartbeat of existence. It is your local rhythm, your small agreement with Earth's gravity, your place in the curve. Somewhere high above you, a satellite clock is ticking a little differently. Somewhere near a collapsed star, time would crawl compared with yours. And here, where you sit, held gently by Earth, every second feels ordinary only because you are moving with it. The deeper truth is softer and stranger. Time does not flow the same everywhere. It listens to gravity, and gravity, quietly, changes the pace at which the universe becomes real. The universe is expanding into nothing, because it isn't expanding into anything. The universe is not growing into a giant darkness outside itself. The stranger truth is that there may be no outside for it to grow into at all. When you imagine expansion, your mind naturally reaches for familiar things. A balloon swelling into a room, smoke spreading through air, water filling a bowl, an explosion throwing pieces into empty space. These images feel useful because they match everyday life, where anything that expands must expand into something else. A city expands into countryside, a cloud expands into sky, a ripple expands across water. But the universe is not an object sitting inside a larger container. It is not a glowing sphere pushing its edge outward through a pre-existing emptiness. In modern cosmology, when we say the universe is expanding, we mean that space itself is stretching, and the distances between faraway galaxies are increasing because the geometry between them is changing. The galaxies are not simply flying outward from one central blast point like sparks from a firework. On the largest scales, space is carrying them farther apart, like marks on a rubber sheet moving away from one another as the sheet itself stretches. This is why there is no special center of expansion that astronomers can point to and say, the universe began over there. Every distant galaxy appears, on average, to be moving away from every other distant galaxy, because all large regions of space are participating in the expansion. If you were in a galaxy billions of light years away, looking out with powerful instruments, you would also see other galaxies receding from you. You would feel, from your own perspective, as if you were near the center. But that would not make you special. It would reveal the deeper rule. In an expanding universe, every observer can see themselves as central, because expansion is not happening from one location into another location. It is happening everywhere space exists. This is one of the hardest ideas to hold because the human imagination wants an edge. We want to picture the universe as a shape with a boundary, and beyond that boundary, maybe empty blackness waiting to receive it. But the universe, especially the whole universe beyond what we can observe, may not have an edge in the ordinary sense. It may be infinite, which means there is no outer wall, no final surface, no border where space stops and something else begins. Or it may be finite, but curved in a way that has no boundary. Somewhat like the surface of Earth is finite in area, but has no edge you can walk to and fall off. That comparison is not perfect. because Earth's surface is two-dimensional, while space is three-dimensional. But it helps loosen the trap in the mind. Something can be limited in one sense without having an edge in the way we expect. The observable universe does have a boundary, but that boundary is not a physical wall. It is a horizon created by time and the speed of light. We can only see as far as light has had time to travel since the early universe became transparent. Beyond that horizon, there may be vastly more universe, perhaps infinitely more. But its light has not reached us, and may never reach us if expansion carries regions away too quickly. So when you ask what the universe is expanding into, the question may be shaped by the wrong picture. It is like asking what is north of the North Pole. The words make grammatical sense, but the map does not work that way. The universe is not expanding into nothing, because nothing is sitting outside it, like an empty room. Rather, the expansion of the universe is the increase of distances within space itself. The Big Bang was not an explosion in space. It was an expansion of space from an earlier hot, dense state. This does not mean every point of space was once packed into one tiny place in a larger void. It means the distances between points were once much smaller, and as the universe evolved, those distances grew. The early universe was hotter and denser everywhere, not because matter was all exploding away from a single location, but because space everywhere was compressed compared with today. As space expanded, light stretched with it. This stretching is one reason distant galaxies appear redshifted. The light traveling through expanding space has its wavelength stretched. So by the time it reaches us, it carries the signature of cosmic expansion. In this quiet clue, the universe tells its story. The light itself has been on a journey through a changing cosmos, and the color shift is like a message written into the travel. But expansion does not mean everything expands in the same way. Your body is not expanding. Earth is not swelling. The solar system is not being pulled apart by ordinary cosmic expansion. Gravity, electromagnetism, and other binding forces hold local systems together strongly enough that expansion matters mainly on the enormous scales between galaxy groups and clusters where space is not tightly bound. This is why the Milky Way can remain coherent while distant galaxies recede. The stretching belongs to the large-scale fabric, not to every object sitting inside it. And this gives the universe a strange double nature. Locally, things can feel stable, bound, familiar. Cosmically, the stage itself is changing. The room you sit in holds its shape. Yet the deep universe beyond our neighborhood is quietly widening. That widening has consequences for the future. Galaxies that are not gravitationally bound to us will drift farther away over immense stretches of time. Some will become unreachable, not because they move through space faster than light locally, but because the space between us and them expands so much that light emitted from them may never cross the growing distance. The universe is not expanding into a destination. It is expanding into its own future. More space is not being poured into a container. Space itself is becoming more spacious. And perhaps this is where the science becomes quietly philosophical. We often imagine existence as something placed inside emptiness, as if reality needs a box to be real. But the universe asks you to release the box. It asks you to imagine a world where space is not the room, but the thing changing, where distance is not fixed, but historical, where outside may not be a place at all. This does not make the universe easier to picture, but it makes it more honest. The deepest truths are not always shaped like human intuition. Sometimes they require you to stop seeing the cosmos as an object and begin seeing it as a whole system of relationships, distances, histories, and horizons. So the next time you hear that the universe is expanding, try not to picture a sphere growing into black emptiness. Picture instead the silent widening of all unbound distances, the slow stretching of light across billions of years, the vanishing of far galaxies beyond horizons we can never cross, and the strange calm of a cosmos that does not need an outside to change. The universe is not moving into nothing. It is not pushing through a wall. It is not looking for a place to go. It is the place, and the place itself is growing. Your body is rebuilt, while you still feel like you. The person you call you is not made from a fixed collection of material. but from a living pattern that keeps replacing its pieces while somehow preserving the feeling of being the same self. This is one of the most quietly unsettling truths about the body. You do not stay physically identical to yourself. You feel continuous because your memories, habits, name, voice, preferences, wounds, and familiar inner narration carry forward. But the biological structure beneath that continuity is always in motion. Cells divide, cells die, proteins are built and broken down, blood cells are replaced, skin cells rise, flatten, shed, and disappear. The lining of your gut renews rapidly because it lives in a harsh world of acid, enzymes, food particles, microbes, and constant friction. Your bones, which feel like the most permanent architecture inside you, are also remodeled by specialized cells that remove old bone and lay down new mineral structure. Even the fat in your body is not static. Molecules move in and out of storage, responding to meals, fasting, hormones, and energy needs. The body is not a statue. It is a city at night, repairing roads while traffic still moves, replacing bricks while the building still stands, changing its materials without announcing the renovation to the person living inside. But this truth needs care, because it is often exaggerated into a simple claim that every atom in your body is replaced every 7 years. That sentence is popular, but it is too neat to be fully true. Different parts of you renew at very different speeds. Some cells are short-lived, such as many cells in the intestinal lining. Red blood cells usually circulate for about 4 months before being replaced. Skin renews continually, though the timing depends on the layer and the person. Bone remodels slowly across years. Some cells in the brain, especially many neurons in the cerebral cortex, can last for much of your life. Certain structures are repaired and maintained rather than completely swapped out on a fixed schedule. So the real story is more interesting than the myth. You are not simply a brand new body every 7 years. You are a layered mixture of the old, the renewed, the repaired, the recycled, and the enduring. You carry cells that are recent, structures that are decades old, and molecular components that may have been replaced many times without disturbing the larger shape of who you are. And yet, through all this turnover, you wake up feeling like one continuous person. That continuity is one of biology's greatest illusions and achievements. Think about your skin. It is your boundary with the world, but it is also a moving surface. Cells are born in deeper layers, gradually pushed upward, changed, hardened, and eventually shed. The dust in a room can contain tiny fragments from human skin, not in a dramatic or frightening way, but as part of ordinary life. You are constantly leaving pieces of yourself behind without feeling diminished. Your blood tells another version of the same story. Red blood cells do not have a nucleus when mature, and they spend their brief lives carrying oxygen through vessels, bending through narrow passages, and helping keep your tissues alive. When they wear out, they are removed and replaced. The you who walked into a room months ago did not have exactly the same population of red blood cells as the you sitting here now. Yet you do not experience that exchange as a change in identity. Your body treats replacement as maintenance. It does not ask whether continuity requires sameness of material. It proves every day that continuity can also mean preserving organization through change. This is visible in bone as well. Bone seems silent and final, but it is active tissue. It responds to stress, pressure, hormones, nutrition, and injury. When you exercise, when you heal from a fracture, when your body balances calcium, your skeleton is participating in a slow conversation with your life. The same is true at the level of proteins. Many proteins inside your cells have limited lifetimes. They are folded, used, tagged, dismantled, and rebuilt. Your body is always manufacturing itself from food, water, oxygen, and stored resources, turning the outside world into the temporary substance of you. The meal you ate becomes energy, structure, signal, warmth, repair. The water you drink becomes blood volume, cellular fluid, chemical environment. The oxygen you breathe helps release energy from nutrients, and carbon dioxide leaves with your breath. You are not closed off from the world. You are a controlled exchange with it. Life is not matter sitting still. Life is matter passing through a pattern. And that raises the deeper question. If so much of your body changes, what exactly stays? Part of the answer is information. DNA in your cells carries instructions. Those cells use those instructions differently depending on their role. A liver cell and a skin cell may share the same genetic library, but they read different chapters. Another part of the answer is structure. Cells maintain membranes, internal scaffolds, chemical gradients, and relationships with neighboring cells. Tissues maintain shape by coordinating growth, repair, and removal. Your nervous system maintains patterns of connection that support memory, skill, and personality, even while the molecules inside those connections are constantly being replaced. The self you feel is not located in one permanent substance. It emerges from organized continuity, the body keeping its form, the brain preserving patterns, the world recognizing your face, your name, your story, and you recognizing them back. This is why change can happen without erasing you. You can heal a cut, grow stronger, lose weight, gain weight, recover from illness, scar, age, learn, forget, and still feel like the same person moving through time. But the sameness is not stillness. It is rhythm. It is renewal with memory. It is a flame that keeps its shape while the fuel changes. And perhaps this is why aging feels so mysterious. You are always being repaired, yet not perfectly. Over time, DNA damage can accumulate. Repair systems can become less efficient. Proteins can misfold. Cells can enter states where they no longer divide properly. Tissues can lose resilience, and the body's rebuilding becomes less exact. Aging is not simply the body failing to replace itself. It is the gradual change in the quality, coordination, and regulation of replacement. The renovation continues, but the blueprints become harder to follow, the workers slower, the materials sometimes less carefully placed. Still, every moment you are alive, your body is performing an act of astonishing persistence. It is defending the pattern of you against entropy, injury, infection, and time. It is rebuilding quietly while you think, sleep, worry, love, and listen. You do not feel most of this work because consciousness is spared the burden of supervising it. Your heart does not ask permission to replace blood cells. Your skin does not ask you to approve its renewal. Your bones do not announce every microscopic repair. The body carries on beneath awareness, and in that hidden labor, there is something almost tender. You are being remade without having to remember how. So when you think of yourself, try not to imagine a fixed object traveling through life unchanged. Imagine a pattern held open by constant work. Imagine a river that keeps its name while the water moves on. Imagine a house whose walls are repaired, whose air is exchanged, whose lights are rewired, while someone inside still recognizes the room. That someone is you, but you are also the house, the repair, the exchange, the memory of form. Your body is rebuilt while you still feel like you, because identity is not made from unchanging material. It is made from continuity through change. And perhaps that is the soft lesson hidden in your cells. To remain yourself, you do not have to stay the same. You only have to keep the pattern alive. You blink away years of your life. Every few seconds, the world disappears behind your eyelids, and almost every time, you fail to notice that it vanished. This is one of the quietest interruptions in human life. The blink. It seems too small to matter, too ordinary to become strange. But if you begin to add those tiny moments together, they form a hidden darkness stitched through your entire existence. Most people blink many thousands of times a day, though the exact number changes with tiredness, attention, emotion, eye dryness, screen use, environment, and even the kind of conversation they are having. Each blink is brief, often only a fraction of a second, but across a day, a year, and then a lifetime, those fractions become hours, days, and eventually years in which your eyes were physically closed. You do not experience life as constantly interrupted because your brain protects the flow. It does not let each blink feel like a cut in the film. Instead, the mind bridges the gap, holding the world steady so smoothly that you feel as if vision has continued without a break. But in the simplest physical sense, you are repeatedly losing the visual world and receiving it back again and again, like a light that turns off so quickly the room still feels illuminated. And the strangest part is that blinking is not just a meaningless habit. It is a necessary maintenance system, a protective rhythm, and perhaps even a quiet punctuation mark in the way the brain manages attention. Your eyes are delicate organs exposed directly to air, dust, wind, light, pollen, dryness, and tiny particles that could irritate or damage them. The front of the eye, especially the cornea, needs to stay moist and smooth for vision to remain clear. Each blink spreads a thin tear film across the eye's surface, like a tiny wave polishing glass. This tear film is not just water. It contains layers that help keep the surface stable, reduce evaporation, wash away debris, and protect against infection. Without blinking, the eye would dry, sting, blur, and become vulnerable. You can feel this if you try to stare without blinking for too long. At first it seems easy, then the pressure builds. The eyes begin to burn. Vision may waver. The body asks for a blink with increasing urgency because the surface of the eye is not designed to remain open endlessly. In this sense, every blink is a small act of repair. It refreshes the window through which you see. It is the body cleaning the lens while you are still using it. But blinking is not only about moisture. There are different kinds of blinks. Some are spontaneous, happening without conscious decision as part of the body's normal rhythm. Some are reflexive, triggered by sudden light, approaching objects, irritants, or threat. If something rushes toward your face, your eyelids close before you have time to politely think about it. This fast protective response is ancient and practical. The eye is too valuable to leave unguarded. Other blinks can be voluntary, like when you deliberately close your eyes or wink. Together, these forms of blinking reveal that the eyelid is not just a curtain. It is a shield, a cleaner, a timer, and a communicator. In conversation, blinking can change with emotion and mental effort. People may blink more during certain kinds of stress, fatigue, or social interaction, and less when they are intensely focused. When you read, watch a screen, drive, play a game, or concentrate on a delicate task, your blink rate may drop, sometimes without you noticing. This is one reason long screen sessions can leave the eyes feeling dry or strained. The eyes are still open, still receiving light, still working, but the usual refreshing rhythm becomes reduced, and the surface suffers quietly. The modern world asks the eyes to stare more than they were built to stare, and blinking pays the price. There is also evidence that blinking may be linked to attention in a deeper way. You often blink at natural breakpoints, after a sentence, during a pause, when shifting from one thought to another, or when the brain has a brief moment to reset. It is as if the mind waits for tiny endings, then lowers the curtain for an instant. A blink may help the brain disengage from one small unit of information and prepare for the next. Not always, not perfectly, but often enough to suggest that blinking is tied to how attention breathes. In that way, your life is not only divided by clocks and calendars, but by thousands of tiny eyelid closures, each one refreshing the eye and perhaps helping the mind move from one fragment of experience to the next. And still, you almost never notice the absence. You notice when a light flickers, when a video cuts, when a signal drops, but you do not notice your own eyelids repeatedly covering your vision. This is because the brain reduces awareness of the darkness. It expects the blink. It knows, in a practical sense, that the disappearance is self-made and temporary. The world does not need to be reintroduced every time your eyes reopen. Your cup is still there. The room is still there. The person speaking is still there. So the brain preserves continuity, not by showing you every missing moment, but by letting your experience glide across them. This is both useful and humbling. Useful, because you would be distracted all day if every blink felt like a blackout. Humbling, because it shows how much of your smooth life depends on hidden editing. You are not watching an unbroken stream. You are living inside a rhythm of disappearance and return. And if you add it all together, the scale becomes haunting. Depending on how often you blink and how long each blink lasts, the total closed-eye time across a long life can reach years, not spent asleep, not spent dreaming, not spent away from the world intentionally, but scattered invisibly through waking life in tiny pieces too brief to remember. A lifetime of micro-darkness, a private night folded into every day. Yet those lost moments are not wasted. They are the cost of clear seeing. They are the maintenance pauses that allow vision to continue. They are the eye's soft reminder that even perception needs rest. So the next time you blink, try to catch it. Notice the world vanish, then return as if nothing happened. Notice how quickly your mind forgives the gap. In that tiny closure, your body protects itself, cleans itself, resets itself, and preserves the illusion of an unbroken present. You blink away years of your life, yes, but those years are not stolen from you. They are given back as sight. The darkness is the price of the image. The interruption is what helps the world remain visible, and perhaps there is something quietly beautiful in that. Even to keep your eyes open to reality, you must keep closing them, again and again, trusting that when the dark lifts, the world will still be there. Your body emits tiny amounts of light. Your body is not dark in the way it seems to be dark. Even now, in a quiet room with the lights off, you are releasing tiny traces of light too faint for human eyes to see. This is not a mystical aura, not a supernatural glow, and not the kind of brightness that would outline your body in the dark like a candle under the skin. It is something quieter, smaller, and in many ways more fascinating. A real biological phenomenon often called ultra-weak photon emission. Living cells carry out chemical reactions constantly. They use oxygen, break down nutrients, build molecules, repair damage, send signals, and maintain the delicate conditions that keep you alive. During some of these reactions, especially reactions linked to metabolism and oxidative processes, tiny amounts of energy can be released in the form of photons, the basic particles of light. Most of this emission is unimaginably faint, far below what your eyes can detect. If you stood in a completely dark room, you would not see your hand glowing, because the light from your body is much weaker than the threshold of ordinary vision. But with sensitive equipment designed to detect extremely low levels of light, scientists have measured faint visible photon emission from living organisms, including humans. This means the phrase "your body emits light" is true, but it must be understood carefully. You are not shining like a lamp. You are whispering in light. The glow is so soft that it belongs more to instruments than to sight, more to biology than to spectacle. It is the body's chemistry, leaving a nearly invisible signature as it works. And the deeper you follow that idea, the stranger your ordinary body becomes. Every second, your cells are managing energy. Inside them, mitochondria help convert food and oxygen into usable energy, and this process is not perfectly quiet. Like any complex chemical system, it produces byproducts. Some of these involve reactive oxygen species, highly active molecules that can participate in chain reactions with fats, proteins, and other cellular structures. When certain molecules are pushed into excited states and then return to lower energy states, a tiny amount of light can be emitted. It is a little like a spark too small to see, happening not as fire but as chemistry. This does not mean the body is malfunctioning. Oxidative reactions are part of life, and the body also has antioxidant systems and repair mechanisms to keep them balanced. The faint light is not simply a sign of damage, but part of the broader story of living metabolism, energy flowing, molecules changing, cells responding, the body constantly negotiating between activity and repair. Even plants, seeds, bacteria, and many other living systems can emit ultra-weak light. Life, in this sense, is not silent at the physical level. It releases traces, it leaves signals, it glimmers at the edge of detectability. And there is another kind of light your body emits much more strongly: infrared radiation. Because your body is warm, it radiates heat, mostly in infrared wavelengths that your eyes cannot see. Thermal cameras can detect this easily and turn it into visible images, which is why people appear bright in thermal imaging. But infrared heat radiation and ultraweak visible photon emission are not the same thing. The infrared glow comes from your body's temperature. The ultraweak visible emission comes from subtle biochemical reactions. One is the warmth of being a living object in a cooler environment. The other is a faint optical trace of cellular chemistry. Both remind you that your body is not a closed, silent mass. It is continuously exchanging energy with the world. You take in sunlight indirectly through food chains, breathe oxygen shaped by ancient life, release heat into the air, and emit tiny light signals that almost no eye could ever notice. The body is not separate from physics. It is physics organized into breath, pulse, hunger, thought, and repair. What makes the ultra-weak glow especially interesting is that it can vary. Measurements have suggested that photon emission from the human body can change with time of day, body region, and physiological state. This makes sense if the light is connected to metabolism, because the body's chemistry follows rhythms. Hormones shift, temperature changes, activity rises and falls, skin blood flow changes. Cells work differently when you are resting, moving, stressed, healing, or exposed to different conditions. Some studies have found that the face may emit slightly more of this faint light than other body regions, possibly because it is metabolically active, exposed, and structurally different from covered areas of skin. But again, this is not something visible to the naked eye, and not something that proves personality, spirituality, or hidden energy fields in the popular sense. It is biology at the edge of light detection. The truth is already strange enough without exaggeration. You are a chemical constellation, but not in the dramatic way a fantasy image might show. You are a warm, breathing system of countless microscopic reactions, and a tiny fraction of those reactions end by releasing photons into the dark. Somewhere between the cell and the skin, between oxygen and repair, between energy and waste, your body produces a glow too faint to become vision. And perhaps that is why the fact feels so quietly powerful. It does not turn you into a magical being. It makes ordinary life feel more exact, more delicate, more connected to the same physical rules that make stars shine, flames flicker, screens glow, and atoms release energy when they change states. Your light is not starlight, not firelight, not daylight. It is lifelight, almost completely hidden, made not for display, but as a side effect of being alive. And if you think about that gently, it changes the way you imagine yourself in darkness. The room may look black, your skin may seem still, your body may feel solid and familiar, but beneath awareness, chemistry continues. Molecules collide, energy shifts, cells repair, heat leaves you, tiny photons escape. You are not glowing for an audience. You are glowing because living matter is never truly motionless. So the next time you turn off the light and lie still, remember this quiet fact. Your eyes may see darkness, but your body is not doing nothing. It is working in hidden brightness, sending out traces so faint they almost disappear into the universe. And maybe that is enough to make the body feel less ordinary. Not because it shines brightly, but because even its smallest invisible signals say the same thing over and over. Life is happening here. Your blood contains iron forged in ancient stars. The red flowing through your veins carries a metal that was born long before Earth existed, in places so hot and violent that your body is, in a very literal sense, using the ashes of ancient stars to stay alive. Every time you breathe in, oxygen enters your lungs and moves into your blood, where it is picked up by hemoglobin, the protein inside red blood cells that gives blood its deep color and its extraordinary ability to carry life from one part of the body to another. At the heart of each hemoglobin molecule are hemigroups, and inside each hemigroup sits an iron atom. That iron is not decorative. It is not a small detail. It is the reason hemoglobin can hold oxygen gently enough to transport it, but not so tightly that it refuses to let go. In the lungs, where oxygen is abundant, iron helps hemoglobin bind oxygen. In tissues that need oxygen, the hemoglobin releases it, allowing your cells to produce the energy that keeps your heart beating, your muscles moving, your brain thinking, and your body warm. So when you feel your pulse, you are not only feeling biology, you are feeling cosmic history doing practical work inside you. The iron in your blood was not created inside your body, and it was not created on Earth. Your body can rearrange iron, store it, recycle it from old red blood cells, and use it again with remarkable efficiency, but it cannot make iron atoms from scratch. Those atoms had to come from the universe's earlier furnaces. In the beginning, after the Big Bang, the universe was mostly made of the simplest elements, especially hydrogen and helium, with only tiny traces of a few light elements. The heavier ingredients needed for rocky planets, oceans, bones, blood, tools, cities, and nervous systems had to be built later inside stars. Stars are not just lights in the sky. They are element-making engines. For most of their lives, stars produce energy by fusing lighter atoms into heavier ones. Hydrogen becomes helium. In massive stars, as the core changes over time and temperature rises, fusion can build heavier elements in stages, like a cosmic ladder being climbed under extreme pressure. Carbon, oxygen, neon, magnesium, silicon, and other elements can form inside the deep interiors of massive stars. But iron is special. It sits near a turning point in the story of fusion. For many elements lighter than iron, fusion can release energy, helping a star hold itself up against gravity. But building elements heavier than iron by ordinary fusion tends to require energy rather than release it. So when a massive star develops an iron-rich core, it is approaching a crisis. Iron does not give the star the same kind of fuel to keep resisting collapse. The core can no longer support itself in the old way. Gravity wins. The star's center collapses, and in the chaos that follows, the outer layers can be blasted into space in a supernova, scattering newly made elements across the galaxy. Not all iron comes from one kind of stellar death. A huge amount of the iron in galaxies is also produced and spread by Type Ia supernovae, which involve white dwarfs in binary systems. These events can create large quantities of iron group elements and seed space with them. The important truth is simple but profound. The iron in your blood was made through stellar processes and delivered into space by ancient stellar explosions and deaths. It drifted, mixed with gas and dust, became part of new clouds, entered the material that formed the sun and the planets, became locked into Earth's crust and oceans and minerals, moved through geological and biological cycles, entered food chains, and finally became part of you. That one iron atom in your hemoglobin may have passed through a story longer than imagination. Born in a star or stellar explosion, thrown into interstellar space, folded into the young solar system, trapped in rock, freed by weathering, taken into living systems, passed through soil, plants, animals, and meals absorbed through your intestine, carried in your bloodstream, stored in ferritin, placed into new red blood cells in your bone marrow, and finally held inside a molecule that helps you breathe. This is not poetry pretending to be science. This is the deep continuity of matter. Your body is not separate from the universe. It is one of the ways the universe has organized its old material into something that can feel, ask, remember, and look back at the stars. And the body treats this ancient metal with care. Red blood cells live for only a limited time, and when they grow old, they are removed mainly by the spleen and liver. The body breaks down hemoglobin, recovers much of the iron, and sends it back for reuse. Iron is precious because you need it, but it can also be dangerous when uncontrolled. Free iron can help drive harmful chemical reactions, so the body usually keeps it bound, stored, transported, and regulated. Too little iron can lead to anemia, leaving a person tired, weak, short of breath, or pale because the blood cannot carry oxygen as effectively. Too much iron can also harm tissues. Life depends not only on having the right elements, but on controlling them with exquisite balance. In this way, the iron in your blood is both cosmic and intimate. It connects supernovae to breath, stellar collapse to heartbeat, galactic chemistry to the warmth of your hands. A star had to live and die before Earth could contain iron in a form that eventually became part of living blood. And yet inside you, that ancient metal is not dramatic. It does not announce its origin. It works quietly, moving oxygen through the dark red rivers of your body while you walk, sleep, speak, heal, and wonder. Perhaps this is what makes the fact so moving. The universe did not simply place stars above you as distant decoration. It placed their remnants within you as function. The same cosmos that burns in the night sky also circulates beneath your skin. You are not made of starlight in a vague inspirational sense. You are made from atoms whose history includes stars, explosions, dust clouds, planets, oceans, and life. The iron in your blood is not a symbol of connection. It is connection. So the next time you take a slow breath, imagine what is happening with gentle accuracy. Oxygen entering the lungs, hemoglobin opening itself to carry it, iron helping hold the fragile exchange, red blood cells moving through branching vessels to deliver what your cells need. And behind that simple breath, imagine the older story. A star reaching the end of its life, matter thrown outward into space, a galaxy enriched, a planet formed, biology rising, and a human body using ancient metal to remain awake for one more moment. Your blood is not just red because of chemistry. It is red because the universe learned, over billions of years, how to turn the death of stars into the possibility of breath. You are breathing molecules, once breathed by dinosaurs. The breath entering your lungs right now may contain particles that once moved through the lungs of creatures that walked under ancient skies. Long before humans existed, long before cities, language, glass, engines, or maps. This idea sounds almost too poetic to be true, as if it belongs more to myth than science, but it comes from a simple fact about Earth. Air does not stay in one place. It travels, mixes, rises, falls, dissolves into oceans, returns from forests, crosses continents, drifts through storms, and spreads through the atmosphere over time until what was once local becomes shared by the whole planet. Every breath you take contains an enormous number of molecules, far beyond anything the mind can comfortably picture. Even a quiet inhale gathers a vast crowd of nitrogen, oxygen, argon, carbon dioxide, water vapor, and many trace gases. Because the atmosphere has been stirred for millions upon millions of years, some of the material in the air around you has almost certainly passed through other living bodies before. Not just other people, not just animals alive today, but ancient organisms too. Mammals that vanished, giant insects, forests that no longer exist, and yes, dinosaurs. This does not mean you are inhaling a magical piece of a specific dinosaur's soul, or that every breath contains a perfectly preserved little packet of prehistoric life. The truth is more subtle and more beautiful. Molecules and atoms are constantly recycled. Some molecules, especially stable gases like nitrogen, can remain in the atmosphere for very long periods, while others are transformed again and again through chemistry, biology, sunlight, water, rock, and living tissue. Oxygen molecules are often split, used, remade and exchanged through photosynthesis and respiration. Carbon atoms may move from air into a leaf, from leaf into an animal, from animal into soil, from soil back into air, from ocean into shell, from shell into rock, then eventually back into circulation. Water molecules can fall as rain, enter a river, freeze, evaporate, become part of a cloud, pass through a plant, or leave an animal's breath as vapor. Earth is not a warehouse where matter sits neatly labeled. It is a turning system, a vast breathing engine. And because dinosaurs lived on this planet for an immense span of time, breathing the same planetary atmosphere, taking in air and releasing it back, the odds become almost unavoidable. Some of the material now entering your body has been inside ancient bodies before. Think of a long-necked sauropod standing near a fern-filled plain, drawing air into a massive chest, while the ground trembles faintly beneath its weight. Think of a small feathered dinosaur darting through undergrowth, breathing quickly as it runs. Think of a predator lifting its head in warm air after rain, lungs filling with the atmosphere of a world that had never heard a human voice. The gases they exhaled did not vanish. They spread. Winds carried them. Plants used some of the carbon dioxide. Oceans absorbed some. Sunlight powered new chemistry. Volcanoes, forests, microbes, and weather kept the planet's materials in motion. Then ages passed. Continents drifted. Species rose and disappeared. Asteroids struck, ice ages came and went, grasslands spread, humans evolved, and through all of it, Earth's atmosphere kept mixing the old with the new. The air in your room is therefore not only today's air, it is ancient air remade into the present. This should change the feeling of breathing. An inhale is not just oxygen entering your body. It is participation in one of Earth's longest exchanges. Your lungs are not separate from the planet. They are part of the planet's circulation. With each breath, your body borrows from the atmosphere, takes what it needs, changes the mixture, and returns something back. You inhale oxygen, and your cells use it to help release energy from food. You exhale carbon dioxide and water vapor, sending part of yourself outward into the shared air. That exhaled breath does not end with you. It will drift away, dilute, mix, perhaps feed a plant, perhaps cross an ocean, perhaps enter another body years from now. In this sense, breathing is never private. It feels intimate because it happens inside your chest, but it belongs to a planetary conversation older than memory. The same atmosphere connects strangers, forests, oceans, animals, cities, and fossils. It connects the living to the extinct, not through fantasy, but through recycling. This is why the idea of breathing molecules once breathed by dinosaurs is so powerful. It reminds you that matter does not respect the boundaries your identity depends on. You think of yourself as a separate body, and in a practical sense, you are. Your skin matters. Your lungs are yours. Your life has a shape no other life has, but the material moving through you is not yours permanently. It is borrowed. The atoms and molecules that help you think, move, and stay warm have had histories before you, and they will have futures after you. Some may have been in ancient rain. Some may have drifted over prehistoric seas. Some may have passed through leaves that no human ever saw. Some may have crossed the lungs of creatures whose bones now sleep in stone. And right now, they are temporarily part of your breath. This does not make you less individual. It makes your individuality more astonishing. Because from shared planetary material, something as specific as you has appeared for a while. You are a temporary arrangement of very old ingredients, breathing a very old sky. The air does not remember the dinosaur, but the journey is real. The molecule does not carry a story in the human sense, but its path belongs to a story larger than any one life. So the next time you take a slow breath, do not imagine air as empty. Imagine it as inheritance. Imagine the atmosphere as a library with no pages, a moving archive of every forest fire, every ocean wave, every leaf, every animal breath, every storm, every vanished era. You are breathing from that archive now, and when you exhale, you add to it. Long after this moment is gone, some part of the air that passed through you may move through another living thing, another landscape, another future mind wondering where it has been. Breathing is not just survival, it is continuity. It is the ancient world entering you quietly, becoming present for a moment, and leaving again. Lightning can be hotter than the surface of the sun. A lightning bolt is not just a flash in the sky. For a fraction of a second, it can heat the air around it to temperatures several times hotter than the visible surface of the sun. That fact sounds almost impossible, because the sun feels like the ultimate image of heat, a glowing star so powerful it warms Earth from millions of kilometers away, while lightning seems brief, thin, and gone almost before your eyes can hold it. But temperature and duration are not the same thing, and this is where the truth becomes fascinating. The visible surface of the sun is roughly around 5,500 degrees Celsius, while the narrow channel of air inside a lightning strike can reach around 30,000 degrees Celsius, depending on the strike and conditions. For one violent instant, the air itself becomes plasma, a state where electrons are torn away from atoms, where ordinary gas is transformed into an electrically charged path, bright enough to carve the night open. Yet because lightning lasts such a short time and occupies such a narrow channel, it does not contain more total energy than the sun's surface in any broad sense. It is not stronger than the sun, it is hotter in that tiny temporary path. That distinction matters, because real science is often more interesting when it is precise. Lightning begins inside storms, where rising warm air, falling ice, water droplets, and turbulent motion help separate electric charges within clouds. The exact details are complex, but the broad idea is that different regions of a storm become electrically unbalanced. One part may build up negative charge, another positive charge, and the ground beneath the storm can become influenced by the cloud's electric field. Nature does not like large electrical imbalance to remain unresolved forever. When the difference becomes strong enough, the insulating air begins to break down. Air normally resists electric current, but under an intense electric field, it can be forced into becoming a pathway. Before the bright flash, you see, invisible or faintly glowing steps of charged air may begin moving downward from the cloud in jagged segments called stepped leaders. At the same time, upward streamers can rise from tall objects, trees, buildings, or even the ground itself. When a connection forms, the main return stroke races upward along the channel, and that is the brilliant flash your eyes recognize as lightning. The light appears to fall from sky to ground, but much of the brightest energy in a cloud-to-ground strike is actually part of this rapid electrical surge moving through the newly formed path. In that instant, electrical energy heats the air so quickly that molecules are violently excited and ionized. The air cannot gently expand. It explodes outward. That sudden expansion creates a shock wave, and as the shock wave travels and weakens, you hear it as thunder. Thunder is not a separate mystery following lightning like an afterthought. It is the sound of air being heated and shoved outward with astonishing speed. The reason you usually see lightning before hearing thunder is simply that light travels much faster than sound. The flash reaches your eyes almost immediately, while the sound takes longer to cross the distance. This is why counting the seconds between flash and thunder can roughly tell you how far away the strike occurred. But the deeper lesson is that lightning briefly turns the atmosphere into a violent electrical instrument. Light, heat, pressure, and sound are all born from the same event. What makes lightning especially strange is how thin and temporary the path is. The bright channel may be only a few centimeters wide in many parts, though the heated region and branching structure can be more complicated, and the total visible bolt can stretch for kilometers. It looks enormous because its light is intense and its path is long, but the hottest part is a narrow thread of transformed air. Imagine a line drawn through the sky by pure electrical imbalance. A line so hot that the air along it stops behaving like ordinary air and briefly becomes a glowing conductor. Then, almost immediately, the channel cools, the light vanishes, and the storm continues as if the sky has closed a wound. That is one reason lightning feels supernatural even when it is entirely natural. It is too fast for ordinary intuition. Your eyes see the result, but not the slow preparation. The growing charge inside the cloud, the invisible electric tension, the first searching pathways. The moment connection becomes possible. By the time you react, the sky has already solved the imbalance with a flash. Lightning also teaches a useful difference between temperature and danger. A spark from static electricity can be very hot in a tiny place, but carry little energy. A warm bath is far cooler, but contains far more heat overall, because it involves a large amount of water. Lightning is dangerous not only because of its temperature, but because of its electric current, explosive heating, shockwave, and ability to travel through air, ground, trees, metal, wiring, plumbing, and human bodies. A strike does not need to hit you directly to injure you. Ground current can spread through the surface after a strike. Side flashes can jump from nearby objects. Conductive paths can carry electricity indoors through wiring or plumbing. This is why storms deserve respect, not fear turned into myth, but informed caution. If thunder is close, the storm is close enough to be dangerous. The safest place is usually inside a substantial building or a fully enclosed vehicle. Not under a tree, not in open fields, not near water, not holding tall metal objects, and not pretending distance makes the sky harmless. Lightning is beautiful, but it is not gentle. And still, beyond the danger, there is wonder in what it reveals about the planet. Earth's atmosphere is not just a layer of air sitting passively above us. It is active, charged, restless, and responsive. Storms are engines that move heat, moisture, and electricity. They build towers of cloud, separate charge, release rain, shake the ground with thunder, and sometimes draw glowing veins across the sky. A lightning bolt is the atmosphere briefly becoming visible as a circuit. It shows you that the air between cloud and ground is not empty in the simple way it looks. It can be stressed, broken open, ionized, and illuminated. It can become a path for energy so intense that for an instant, a piece of the sky becomes hotter than the face of the sun. But unlike the sun, lightning has no long life. It does not burn steadily. It appears, spends itself, and disappears. Its power is not in endurance, but in suddenness. Its beauty is not in warmth, but in rupture. And perhaps that is why it has always held human attention. Long before people understood plasma, charge separation, or return strokes, they knew lightning was a message from the sky that could not be ignored. Now we know it is not a god's weapon or a supernatural sign. It is physics written in light. It is the atmosphere correcting an imbalance through heat, electricity, and sound. So the next time a storm rolls in and the horizon flashes white for a heartbeat, remember what you are seeing. Not just weather, not just brightness. You are watching air become plasma, silence become thunder, invisible charge become visible power. You are watching the sky draw a line so hot it briefly outshines ordinary imagination, then erase it before the mind can fully arrive. Lightning is hotter than the surface of the sun for only a moment, but that moment is enough to remind you that the ordinary air above your head is capable of becoming fire without flame, light without lamp, and sound loud enough to make the earth itself seem to answer. Space has no sound, but planets can create radio songs. If space had ears, it would not hear a roar, a whisper, or a scream. Yet some planets still fill the invisible universe with signals so rhythmic and strange that, when translated, they can sound like songs. This begins with a simple but easily misunderstood truth. Ordinary sound needs something to travel through. On Earth, sound moves by making air molecules push and pull on one another in waves. Underwater, it moves through water. Press your ear to a wall, and vibration can move through solid matter. But in the near vacuum of space, there is no thick, continuous medium like the air around you. So a human voice, an explosion, or a ringing bell would not travel outward as sound in the familiar way. If you were floating outside a spacecraft without a radio, you could not shout to someone nearby and expect your words to cross the emptiness. Your vocal cords could vibrate, but there would be no surrounding air to carry that vibration from your mouth to their ears. This is why the dramatic sounds of spaceships and blasts in movies are artistic choices, not literal space acoustics. Space is not completely empty, of course. It contains thin gas, dust, charged particles, magnetic fields, radiation, and streams of plasma flowing from the sun. But it is far too thin for ordinary sound, as we know it to move the way it does through air. And yet, this silence is not simple nothingness. Space is silent to ears, but not silent to instruments. Planets with magnetic fields can interact with charged particles from the sun, with their own moons, with rings, with radiation belts, and with surrounding plasma. These interactions can create radio waves and plasma waves, which are not sound waves in air, but electromagnetic or charged particle disturbances that spacecraft can detect. When scientists take those measurements and convert them into frequencies our ears can hear, the result can be eerie. Whistles, pulses, rising tones, crackles, groans, chirps, and ghostly hums that feel like the hidden voice of a planet. But it is important to say this carefully. Jupiter is not literally singing through air, and Saturn is not playing music in the vacuum. The songs are translations. They are data made audible. They are invisible waves turned into sound for human understanding. Jupiter is one of the most famous examples, because it has an enormous magnetic field and powerful radio emissions. Some of Jupiter's radio bursts are connected to its moon Io, a volcanically active world that moves through Jupiter's magnetic environment like a generator stirring a giant electrical system. Charged particles spiral along magnetic field lines, Auroras flare around Jupiter's poles, and radio emissions pour outward into space. If converted into audio, some of these signals can sound like waves crashing, birds calling, or distant electronic storms. Saturn also produces radio emissions, including patterns linked to its auroras and magnetic environment. Spacecraft such as Voyager and Cassini helped reveal that planets are not just silent balls moving around the sun. They are electromagnetic worlds, surrounded by invisible structures that can pulse and fluctuate. Earth has its own version of this hidden music. Around our planet, charged particles trapped and guided by the magnetic field can produce waves sometimes called whistlers or chorus emissions. When converted into sound, they may resemble descending whistles or dawn birdsong. These are not poetic names chosen at random. The audio translations can genuinely feel alive, as if the magnetosphere is full of strange creatures calling in the dark. But what you are really hearing is the behavior of charged particles and fields, a kind of space weather made audible. This matters because these waves are not only beautiful, they help scientists understand radiation belts, auroras, particle motion, and the way the sun's activity affects planets. The sun constantly releases a flow of charged particles known as the solar wind. When that flow reaches a planet with a magnetic field, the field can deflect, trap, guide, or energize particles. Near the poles, some particles can enter the upper atmosphere and create auroras, glowing curtains of light. The same broad system that paints auroras can also produce electromagnetic signals, so a planet's song is often tied to its magnetic personality. A dead, airless rock with no strong magnetic field does not speak in the same way as a giant planet wrapped in powerful radiation belts and rotating magnetic fields. The song depends on structure, motion, charged particles, and environment. It is less like a flute playing in air and more like a storm inside invisible geometry. There are also true sound waves in special places beyond Earth, but they still need a medium. Inside the atmospheres of planets, sound can travel. On Mars, for example, microphones on landers and rovers have recorded real sounds carried through the thin Martian air, though they behave differently because the atmosphere is much thinner and mostly carbon dioxide. Inside the Sun and other stars, pressure waves can move through plasma, and scientists can study vibrations to learn about what is happening inside them. Even huge clouds of gas in space can carry pressure waves in a very different, extremely stretched out sense. But when most people say space has no sound, they mean that the open vacuum between worlds cannot carry familiar audible sound to your ears. That remains true. The surprise is that silence does not prevent the universe from having patterns. It only means you need the right instrument to notice them. Human ears are narrow tools, built for air, conversation, footsteps, warnings, music, and the small acoustic world of Earth. Radio antennas, magnetometers, and plasma wave instruments are different kinds of ears. They listen to what your body cannot. They reveal that planets are surrounded by invisible activity, particles streaming, fields vibrating, radiation shifting, magnetic regions breathing under pressure from the sun. When we turn those measurements into audio, we are not making the universe more magical by lying about it. We are making its real invisible behavior available to human senses. We are giving the mind a doorway into data it could never feel directly. And perhaps that is why planetary radio songs are so haunting. They remind you that silence is not the same as stillness. A planet can appear quiet in a telescope while its magnetic field is alive with motion. A moon can move through a giant planet's invisible environment and help trigger radio bursts across millions of kilometers. The space around Earth can seem empty, while charged particles trace hidden paths above your head. The universe does not need air to be expressive. It has other languages: light, radio, magnetism, plasma, gravity, radiation. Sound is only the language your ears happen to inherit. So the next time you imagine space as silent, keep the silence because it is real, but let it become deeper. It is not the silence of absence. It is the silence of a world speaking in forms your body was not built to hear. Somewhere, Jupiter's magnetic field is pulsing. Saturn's auroral regions are shifting. Earth's radiation belts are whispering in waves. Space has no sound for an unaided human ear. But with the right instruments, the planets become choirs of invisible motion, singing not through air, but through the hidden electrical life of the cosmos. The same water has been recycling for billions of years. A glass of water looks like something new when you lift it to your lips, but much of the water on Earth has been moving through oceans, clouds, ice, rivers, rocks, bodies, storms, and deep time for billions of years before it ever reached you. It may have fallen as rain over a forest that no longer exists, frozen into ancient ice, passed through the roots of plants, flowed through the bloodstream of animals, rested in the dark underground as groundwater, steamed from a volcanic landscape, or rolled as a wave across an ocean under a sky no human had ever seen. Water is not manufactured fresh each morning for the modern world. Earth's water is part of an immense planetary cycle, constantly changing location and form while remaining, in a broad sense, the same ancient material. The water in your cup may feel ordinary because it is clear, quiet, and familiar, but it is older than every city, older than every language, older than the bones of our species, older than the first human story ever told. Some of Earth's water likely arrived or formed very early in the planet's history, connected to material from the young solar system, with contributions from water-rich minerals, impacts from asteroids or similar bodies, and volcanic outgassing from Earth's interior. Scientists still study the exact proportions and timing, but the deep truth is clear. Earth has held and recycled water across nearly its entire history. The same planet that once had a young, violent surface eventually cooled enough for oceans to form, and since then, water has been moving through a long cycle of transformation. It evaporates from oceans, lakes, soils, and leaves. It rises as invisible vapor. It cools and condenses into clouds. It falls as rain, snow, sleet, or hail. It flows across land as streams and rivers. It sinks into soil and becomes groundwater. It freezes in glaciers. It enters living organisms. It returns through breath, sweat, waste, decay, and evaporation. It is lifted by sunlight and pulled by gravity. The water cycle is not just a school diagram with arrows. It is one of Earth's oldest rhythms, a continuous exchange between sky, land, ocean, ice, rock, and life. But this story becomes more interesting when you realize that not all water moves at the same speed. Some water returns quickly. A drop that evaporates from the ocean may fall as rain days later. A puddle may vanish in sunlight and rejoin the atmosphere within hours. Water in a river may travel to the sea in weeks or months, but groundwater can remain underground for years, centuries, or even much longer. Deep groundwater in some places can be thousands to millions of years old. Ice locked in glaciers and ice sheets can preserve water from ancient climates, holding tiny bubbles and chemical clues that scientists use to study past atmospheres. The ocean itself is a vast reservoir where water mixes over long periods, carrying heat, salt, nutrients, and life around the globe. So when you drink water, you are not just drinking something recycled once. You are drinking from a system with many clocks. Some of its journey may be recent. Some of it may be unimaginably old. A water molecule is simple in structure, made from hydrogen and oxygen, but its path can be incredibly complex. It may join the ocean, separate through evaporation, fall as rain, become part of a leaf, enter fruit, move into an animal, return to soil, seep into stone, emerge from a spring, enter a river, and eventually reach a treatment plant before flowing from a tap. Along the way, it can be filtered, dissolved with minerals, frozen, boiled, purified, polluted, cleaned, and transformed by living systems. And here, we should be precise. When people say the same water has been recycling for billions of years, they do not mean every individual water molecule has remained unchanged forever in a perfect, unbroken chain. Some water molecules are split apart during chemical reactions, especially in biological and geological processes, and later hydrogen and oxygen can recombine into water again. Plants split water during photosynthesis, using sunlight to help build sugars and releasing oxygen. In the upper atmosphere, sunlight can break molecules apart. Inside rocks and minerals, water can be stored, released, or chemically bound. So the water cycle is not only a movement of intact droplets, it is also a chemical story. Still, the atoms and molecules of Earth's water are continually reused, reshuffled, and returned. The water you drink belongs to a planetary inheritance that has not been used up, only changed. That is what makes water so powerful. It is both temporary and enduring. It never stays yours, yet it never truly leaves Earth's great circulation. Your body borrows water for a while. It becomes blood plasma, cellular fluid, saliva, sweat, tears, the chemistry of digestion, the moisture in breath. It helps regulate temperature, carry nutrients, cushion organs, support reactions, and keep cells alive. Then it leaves you. Some leaves through urine, some through sweat, some through the air you exhale, some through the natural turnover of the body. You do not own the water inside you. You host it. You become a brief chapter in its long biography. This should change the feeling of a simple drink. The water passing over your tongue is not passive. It has carried minerals from rock, risen through clouds, fallen through air, carved valleys, fed roots, shaped weather, cooled lava, moved through oceans, and helped life survive mass extinctions and climate shifts. Water is one reason Earth is not just a dry stone orbiting the sun. It softens landscapes, transports chemistry, stores heat, supports cells, and makes life possible in forms both obvious and hidden. Even deep beneath the surface, water can move through cracks and pores in rock, affecting minerals, pressure, and sometimes the conditions where unusual microbial life can persist. Water is not merely something life uses. It is part of the way Earth becomes livable. And because it recycles, it connects moments that seem completely separate. A raindrop on your window may have once been sea mist. A sip from a bottle may include water that spent time in a glacier. A river may carry ancient groundwater mixed with yesterday's rain. The boundaries we place around water, this cup, that lake, this cloud, that tear, are temporary shapes in a much larger motion. The same substance keeps changing costume. Liquid becomes vapor, vapor becomes cloud, cloud becomes rain, rain becomes river, river becomes sea, sea becomes sky again. It is one of the planet's great acts of remembering without a mind, and perhaps that is why water feels so ordinary and sacred at the same time. You need it every day, so you stop noticing it. But when you slow down and follow its history, it becomes almost impossible to see it as simple. The water in your hand is older than your hand, older than the glass holding it, older than the civilization that cleaned and delivered it. It has no memory in the human sense, but it has a path. It has touched ages you can only imagine, so the next time you drink, pause for a breath before swallowing. This is not just a refreshment. It is ancient Earth passing through you. It is sky, stone, ocean, ice, root, river, and cloud becoming part of your living body for a little while. You are not separate from the water cycle. You are one of its temporary homes. Your skin is covered in invisible ecosystems. Your skin may look like a single surface, but it is closer to a living landscape, covered in invisible communities that build tiny worlds in every fold, pore, crease, and patch of warmth. When you look at your arm, you see skin as a boundary, the place where you end and the outside begins. It seems smooth from a distance, quiet, personal, almost empty unless there is a freckle, a hair, a scar, or a drop of sweat. But under a microscope and through modern genetic tools, that surface becomes far more crowded and alive than your eyes could ever guess. Your skin is home to bacteria, fungi, viruses, and even microscopic mites. Most of them too small to notice, many of them harmless, some of them helpful, a few capable of causing trouble when the balance shifts. This is called the skin microbiome, and it is not a dirty accident sitting on top of you. It is part of the normal biology of being human. Different areas of your body create different habitats, almost like different climates on one planet. The oily skin of the face, scalp, chest, and back supports microbes that thrive around sebum, the oily substance produced by sebaceous glands. Moist areas like the armpits, groin, and spaces between toes offer warmth, sweat, and shelter, favoring different communities. Dry areas such as the forearms or legs tend to host yet another set of organisms, adapted to lower moisture and fewer nutrients. So your body is not covered by one invisible ecosystem, but many. Your forehead, elbow, armpit, palm and heel are not the same world to a microbe. They are separate neighborhoods with different chemistry, temperature, acidity, oil, salt, friction, and oxygen levels. Even the skin's slightly acidic surface, sometimes called the acid mantle, helps shape which organisms can live there. It discourages some harmful invaders while allowing familiar residents to remain. This means your skin is not simply a wall, it is a managed border, a living border, where your body and microbial life constantly negotiate. Some of these microbes help protect you by taking up space and resources that more harmful organisms might otherwise use. They can compete with invaders, produce substances that limit pathogen growth, and communicate with your immune system in subtle ways. Your immune system does not simply attack everything on the skin. It learns. It has to recognize the difference between ordinary residents, harmless visitors, and genuine threats. That education begins early in life and continues as your environment, hygiene habits, age, hormones, health, climate, clothing, and skincare choices change. In this sense, your immune system is not guarding an empty castle. It is managing a crowded city at the gate. Too little response, and harmful organisms may overgrow. Too much response, and the body may become inflamed, irritated, or reactive. Skin health depends on balance, not sterility. This is why the idea that all microbes are enemies is too simple. Cleanliness matters, especially to reduce disease transmission, remove harmful contamination, protect wounds, and prevent infection. Washing your hands is one of the most important public health practices ever discovered. But the goal of healthy skin is not to erase all microbial life forever. That would be impossible, and it would not necessarily be good. Your skin's residents return quickly because they are part of your biology and environment. Every surface you touch, every fabric you wear, every place you visit, every person you live near, can influence the microbial mixture around you. Even pets, soil, plants, and indoor spaces can contribute to the microbial world your skin encounters. The invisible life on you is shaped by your visible life, and this ecosystem can be disturbed. Antibiotics, harsh cleansers, excessive dryness, injury, illness, humidity, sweat trapped under clothing, and changes in hormones can shift the balance. Sometimes a normally harmless resident can become a problem if it grows too much, enters a wound, or finds the right conditions. Staphylococcus epidermidis, for example, is often a common skin resident and can play protective roles, but related species or certain situations can cause infection. Staphylococcus aureus can live on some people's skin or in the nose without causing immediate illness, yet it can also cause infections when conditions allow. Cutibacterium acnes lives in oily follicles and is linked to acne, but acne is not simply caused by being unclean. It involves oil production, plugged follicles, inflammation, hormones, immune response, and microbial activity together. Malassezia, a type of yeast commonly found on skin, is also a normal resident, but in some contexts it can contribute to dandruff or other skin conditions. The truth is not that microbes are good or bad in a simple way. The truth is ecological. The same organism can be peaceful in one setting and troublesome in another. Location, quantity, immune response, and skin condition all matter. This is what makes the skin feel less like a flat covering and more like a rainforest made of invisible relationships. There are predators, competitors, settlers, resources, signals, borders, and disturbances. There are stable communities and sudden blooms. There are quiet alliances your body depends on without ever informing you. Even tiny mites called demodex live in human hair follicles, especially on the face, and most adults carry them without noticing. For many people, they cause no obvious harm, simply living out their microscopic lives in a world of pores and oils. It sounds unsettling at first because the mind does not like imagining a face as habitat, but discomfort often comes from the illusion that the body should be completely empty of other life. It never was. To be human is to be a host, not in a frightening sense, but in a biological one. You are an individual, yes, but your body is also an environment. Your skin is not lonely, it is inhabited, and that inhabited surface is constantly doing work, holding in water, keeping out many threats, sensing pressure and temperature, repairing itself after cuts, producing oils and sweat, supporting immune surveillance, and cooperating with microbial residents that help maintain the boundary. When the skin barrier is damaged, the whole ecosystem can change. Dryness can lead to cracks. Cracks can invite irritation. Irritation can change immune activity. Changed immune activity can alter microbial populations. Altered microbes can worsen inflammation. This loop is one reason conditions like eczema can involve both barrier problems and microbial imbalance. The skin is not just a passive victim in these conditions. It is an ecosystem under stress. And perhaps this is where the subject becomes quietly philosophical. You may think of yourself as a single being wrapped in skin, but the skin itself reminds you that life is layered. Your identity feels singular from the inside, yet your body is made possible by cooperation with things that are not exactly you. The line between self and world is real enough to protect you, but it is not as absolute as it feels. You are constantly exchanging signals with organisms you cannot see. You feed some of them with oils and sweat. They shape the chemical environment around you. Your immune system listens to them. Your habits influence them. Their balance influences you. And all of this happens without drama, without a sound, beneath the ordinary feeling of having skin. So the next time you wash your hands, touch your face, feel sweat cooling on your neck, or notice the quiet texture of your palm, remember that the surface of your body is not empty territory. It is a living frontier. It is a city of microscopic neighbors, a shifting map of warm valleys and dry plains, oily shelters and salty streams, defended gates and fragile treaties. You do not need to fear it, and you do not need to romanticize it. You only need to understand it. Your skin is not just covering life, it is carrying life. And in that invisible ecosystem, your body is practicing one of nature's oldest lessons. Survival is rarely a matter of being alone. More often, it is the art of living in balance with what lives beside you. Your brain uses more energy than its size suggests. Your brain is only a small part of your body's weight, yet it behaves like one of the most demanding engines you carry, quietly consuming a surprising share of your energy, even when you are doing nothing at all. You can sit still in a chair, close your eyes, let your hands rest, and feel as if the body has entered a low power mode, but inside your skull the lights do not go out. The adult human brain is only about 2% of body mass, yet it commonly uses around 20% of the body's resting energy. That is not because every thought is dramatic, or because intelligence burns like a visible flame, but because the brain is constantly maintaining the conditions that make thought, sensation, memory, movement, emotion, and awareness possible. A muscle can relax between actions. Your hand can stop gripping. Your legs can stop walking. But the brain cannot simply pause its basic work without danger. Neurons have to maintain delicate electrical differences across their membranes. They have to keep ions in the right places, restore balance after signals pass, recycle chemical messengers, support communication at synapses, and remain ready to respond at any moment. Much of the brain's energy is spent not on spectacular moments of genius, but on the quiet maintenance of readiness. In a way, your brain is like a city that must keep its power grid running through the night. Not because every building is crowded, but because the whole system must be prepared for life to continue when morning arrives. This energy mainly comes from glucose and oxygen delivered by the blood. Your brain does not store large amounts of fuel compared with its needs, so it depends on a steady supply. That is why blood flow to the brain is so carefully regulated, and why interruptions can become serious so quickly. When brain cells are deprived of oxygen and fuel, they cannot maintain their electrical and chemical balance for long. The same energy that lets you solve a problem also lets you recognize a voice, regulate breathing, coordinate balance, interpret pain, understand language, control attention, and keep track of your body in space. But here is the stranger part. Thinking harder does not usually multiply the brain's energy use in the dramatic way people imagine. Solving a difficult puzzle may slightly change where energy is used, increasing activity in some networks and reducing it in others. But the brain is already expensive at baseline. The real cost is being a brain at all. Your ordinary resting mind is not empty. Even when you are not focused on a task, networks inside the brain remain active. They may be involved in memory, self-reflection, imagining possible futures, monitoring the body, maintaining awareness, and preparing for what may happen next. The brain is not a lamp that turns on only when you think. It is more like weather, always moving, always shifting pressure, always forming patterns even when the sky appears calm. This helps explain why mental fatigue can feel so real even without physical movement. When you spend hours making decisions, focusing on screens, filtering distractions, learning new material, or managing emotion, the tiredness may not come from energy use in the same simple way. Tired legs come from climbing stairs. It also comes from attention systems being strained, motivation changing, chemical signaling shifting, and the brain trying to protect itself from endless demand. Concentration is not just using willpower. It is the act of keeping certain networks stable while suppressing others, resisting distractions, holding information in mind, and guiding behavior toward a goal. That control has limits. This is one reason sleep matters so deeply. Sleep is not just a shutdown. During sleep, the brain changes its activity patterns, supports memory processes, regulates emotional systems, and helps maintain the body's internal balance. It also appears to support waste clearance through fluid movement around brain cells, a process scientists continue to study carefully. Your brain's high energy demand means it produces waste and needs recovery. Rest is not laziness to the nervous system. Rest is part of maintenance. The energy story also reveals why the brain is so closely tied to the body. We often imagine the mind floating separately, like a private world above biology. But thought is deeply physical. Every memory you revisit, every word you understand, every image you imagine, every fear that rises in the chest depends on cells using energy. Consciousness does not hover outside metabolism. It is supported by metabolism. A sentence becomes meaningful because neurons signal. A face becomes familiar because networks compare patterns. A decision becomes possible because electrical activity, chemistry, blood flow, and past learning all meet in one living system. Even the feeling of being calm has a biological cost. Your brain must regulate threat responses, body signals, breathing, posture, attention, and emotion. Peace is not the absence of work. Peace is work that has become balanced. This is especially striking in childhood, when the developing brain can use an even larger share of the body's energy than in adulthood, because growth, wiring, learning, and refinement are happening intensely. A child's brain is not simply a smaller adult brain. It is an active construction site, building connections, pruning others, adapting to language, movement, social cues, and the rules of the world. Energy becomes experience, and experience shapes structure. Over time, the brain becomes more efficient, but it never becomes cheap. Even in adulthood, it remains a costly organ, and evolution would not keep such a costly organ unless it offered enormous advantages. The brain lets a body predict, plan, cooperate, remember danger, imagine tools, read faces, learn from mistakes, and create meaning from sensation. Its expense is the price of flexibility. A creature with a powerful brain can adapt not only through claws, speed, or armor, but through understanding. And perhaps that is the most humbling part. The soft tissue inside your skull, fragile enough to need bone around it, is one of the hungriest parts of you because it is constantly building the world you live in. It takes sugar, oxygen, blood, sleep, and silence, and turns them into attention. Language, memory, music, grief, curiosity, and the quiet sense that there is someone here experiencing all of this. So the next time you feel your mind wandering while your body sits still, remember that stillness is not idleness. Behind your forehead, billions of cells are maintaining tiny electrical storms, restoring chemical balance, sending signals, listening for change, and holding together the invisible conditions of awareness. Your brain uses more energy than its size suggests because it is not merely an organ inside the body. It is the body's interpreter, predictor, storyteller, guardian, and dreamer. And every thought you have, even the softest one, is carried by a living engine that never truly stops working while you are alive. The sun loses millions of tons every second. The sunlight touching your face is not free. Every second, the sun pays for that light by losing millions of tons of its own mass. This sounds impossible at first because the sun feels eternal from the human point of view, a constant golden presence that rises and sets. Warm skin, feeds plants, drives weather, and marks the rhythm of days as if it were simply burning in the sky without cost. But the sun is not a magical lamp. It is a star, and a star shines because deep in its core, under crushing pressure and unimaginable temperature, matter is being transformed. The sun's center is so hot and dense that hydrogen nuclei are forced close enough to fuse into helium. This process is called nuclear fusion, and it is the reason daylight exists. But fusion does not simply rearrange matter and leave everything exactly equal afterward. A tiny fraction of the mass involved becomes energy. That energy begins as gamma rays and fast-moving particles in the core, then slowly works its way outward through the sun's interior, being absorbed and re-emitted countless times before eventually escaping from the surface as sunlight. The light that reaches your eyes today may have begun its journey in the sun's core long before you were born, because energy can take a very long time to wander outward through the dense solar interior before crossing the empty distance to Earth in only about 8 minutes once it finally escapes. And hidden inside that journey is the astonishing truth. The sun loses roughly 4 million tons of mass every second through the energy it radiates into space. It also loses additional material through the solar wind, a stream of charged particles flowing outward from the sun, so the total mass loss is even greater. Millions of tons per second sounds catastrophic, as if the sun should be visibly shrinking before us. But the sun is so enormous that this loss is tiny compared with its total mass. It is like removing a spoonful of water from an ocean and expecting the shoreline to vanish. The scale of a star makes human intuition unreliable. 4 million tons is beyond ordinary imagination, but to the sun it is a whisper. Over human history, the sun has lost a vast amount of mass, yet compared with its whole body, it remains almost unchanged. This is why the sun can keep shining for billions of years. It has already been shining for about 4.5 billion years, and it has enough hydrogen in its core to continue its main stable phase for billions more. Still, the fact remains, the warmth on your skin, the blue sky above you, the green of forests, the motion of clouds, the food on your plate, even the ancient sunlight stored in fossil fuels, all come from a star slowly spending itself. Daylight is the visible form of sacrifice written in physics, but we should be careful with the word burning. The sun is not burning like wood in a fireplace. Fire on Earth is a chemical reaction, where atoms rearrange and release energy by combining with oxygen. The sun's power is far deeper. In nuclear fusion, the nuclei of atoms themselves are involved, and the energy released is far greater than chemical burning could ever provide. If the sun were powered by ordinary fire, it would have run out long ago. Instead, its core is a natural fusion furnace, held together by gravity. Gravity tries to crush the sun inward, and the heat and pressure created by fusion push outward. The sun survives as a balance between collapse and expansion, a vast glowing equilibrium. Every second, gravity presses, fusion answers, and the star holds itself open. That balance is not stillness. It is a continuous act. The sun is stable because it is constantly changing in just the right way. This is one of the quiet lessons stars teach. Endurance does not always mean remaining untouched. Sometimes endurance means spending yourself at a rate slow enough to last. The energy released in the core does not simply appear at Earth as brightness. On its way outward, it helps maintain the sun's structure, heats layers of gas, stirs convection near the outer regions, and eventually emerges from the photosphere, the visible surface we see. From there, Sunlight spreads in every direction. Only a tiny fraction reaches Earth, but that tiny fraction is enough to run the climate system, evaporate water, drive winds, fuel photosynthesis, and support nearly every food chain on the planet. Plants capture a small part of sunlight and use it to build sugars from carbon dioxide and water. Animals eat plants or eat other animals that depend on plants. Your body, in a very practical sense, runs on energy that once came from the sun. Even when you move your hand, think a thought, or listen to these words. The energy supporting your body is linked to sunlight stored in food. This means the sun's mass loss is not an abstract number in space. It is part of your metabolism. It is part of weather, agriculture, oceans, forests, and breath. The sun becomes energy. Energy becomes Earth's living systems. Living systems become you. And yet, the sun does not choose this. It is not generous in a human way. It shines because the laws of physics allow matter under extreme conditions to become light. The beauty is that life has learned to live from that process. We exist in the gentle distance where the sun's violence arrives softened. Near the core, fusion is extreme. At Earth, it becomes morning. In space, the sun releases an immense flood of radiation in many forms, from visible light to ultraviolet and infrared, and its magnetic activity can produce flares and coronal mass ejections that affect space weather. The solar wind blows outward, shaping a vast bubble around the solar system called the heliosphere, a region influenced by the sun's particles and magnetic field. So the sun is not only losing mass as light, it is also breathing material into space. Tiny particles stream outward, passing planets, interacting with magnetic fields, sometimes helping create auroras when charged particles are guided into polar atmospheres. The same star that calmly lights your window can also disturb satellites, power grids, and radio communication during strong solar storms. It is peaceful from a distance, but it is not quiet. It is a living star in the physical sense, active, magnetic, turbulent, changing. Still, none of this should make you afraid that the sun is about to disappear. The numbers are dramatic because stars are dramatic, not because the end is near. The sun's future is measured in billions of years, not human lifetimes. Eventually, as hydrogen in the core is depleted, the sun will change. It will leave its current stable phase and become a red giant, transforming the inner solar system in ways far beyond human survival. But that is not tomorrow's story. Today's story is more intimate. The sun is losing millions of tons every second, and that loss is what allows you to see. There is something almost impossible to hold in this. Destruction at one scale becomes life at another. The sun's mass becomes light. Light becomes warmth. Warmth becomes weather. Light becomes photosynthesis. Photosynthesis becomes food. Food becomes movement, memory, repair, and consciousness. A star far away is continuously turning a small part of itself into the conditions for your ordinary day. When you stand outside in sunlight, you are standing in the after effect of nuclear fusion, wrapped in energy that began in a place no human body could survive for even an instant. It has crossed the solar interior, crossed space, entered Earth's atmosphere, scattered into blue sky, warmed the ground, touched your skin, and become part of the quiet feeling of being alive. So the next time sunlight falls across your room, try to feel the scale hidden inside that softness. It is not just brightness, it is mass transformed into energy, a star slowly becoming less of itself so the solar system can remain lit. The sun loses millions of tons every second, and yet from that loss, gardens grow, oceans move, seasons turn, and your body finds the energy to breathe. The most familiar light in your life is also one of the universe's deepest exchanges. Matter becoming radiance, distance becoming warmth, and a star's slow disappearance becoming the reason the world can wake. A day on Earth is not exactly 24 hours. The day you trust as exactly 24 hours is actually a careful average, a human-made smoothing of a planet that never turns with perfect simplicity. You wake up, read a clock, watch morning become noon, noon become evening, and it feels as if Earth is keeping a steady rhythm beneath you, rotating like a flawless machine. One full turn, one clean day, again and again. But nature is rarely that neat. The first surprise is that there is more than one kind of day. If you measure how long Earth takes to spin once compared with distant stars, you get what is called a sidereal day, and it is about 23 hours and 56 minutes. That is the time Earth needs to complete one rotation relative to the far background of space. But the day your life follows is not measured by distant stars. It is measured by the sun. Sunrise, noon, sunset. The return of daylight to the same part of the sky. That is called a solar day, and the average solar day is what we define as 24 hours. The reason these two are different is that Earth is not only spinning, it is also moving around the sun. By the time Earth finishes one rotation relative to the stars, it has also traveled a little farther along its orbit, so it must rotate a little extra for the sun to appear in the same position in the sky again. That extra turn is only a few minutes, but it is enough to separate star time from sun time. So even before we talk about tiny irregularities, the idea of a day has already split into layers. A day is not just one spin. It depends on what you are measuring against. And then the story becomes even stranger, because even the solar day is not exactly the same length every day of the year. The sun does not move across our sky at perfectly uniform speed. Part of this comes from Earth's orbit, which is not a perfect circle but slightly elliptical. Earth moves a little faster in its orbit when it is closer to the sun and a little slower when it is farther away. Another part comes from Earth's tilted axis. Because our planet is tilted, the sun's apparent motion across the sky changes throughout the year, in a way that makes solar noon arrive a little early or a little late, compared with a perfectly regular clock. These effects combine into what is called the equation of time, and it is why a sundial and a mechanical clock do not always agree. A sundial follows the apparent sun, the real sun, as it seems to move through the sky from day to day. A clock follows a smoothed-out version called mean solar time. The difference can reach many minutes across the year. This means that noon by the sun and noon by the clock are not always the same thing. The clock gives you order. The sky gives you a more complicated truth. Human timekeeping is built by averaging the unevenness of the heavens into something society can use. Trains, phones, schools, markets, and meetings need regular hours, not a sun that drifts slightly ahead and behind through the seasons. But beneath that social regularity, Earth is still moving with elegant imperfection. Even the length of Earth's rotation itself changes slightly. The planet is not a rigid metal ball spinning in isolation. It has oceans that slosh, an atmosphere that shifts, ice that melts and freezes, a liquid outer core moving deep inside, earthquakes that redistribute mass, winds that push against mountains, and tides raised mainly by the moon and also by the sun. All of these can affect rotation in tiny ways. Some changes are short-term and irregular, measured in milliseconds or fractions of milliseconds. They are too small for your body to feel, but precise instruments can detect them. Earth's rotation is also gradually slowing over long timescales because of tidal interactions, especially with the moon. The moon raises tides on Earth, and the friction of those tides transfers some of Earth's rotational energy into the moon's orbit, causing Earth's spin to slow very gradually while the moon slowly moves farther away. This is not something that changes your day in any noticeable way from one year to the next, but across hundreds of millions of years, it matters. In the distant past, Earth's days were shorter. Ancient corals and other geological evidence suggest that long ago, there were more days in a year because each day was shorter. The year itself, the time Earth takes to go around the sun, was not dramatically different in the same way, but Earth spun faster, so more rotations fit into one orbit. Imagine a prehistoric Earth where sunrise and sunset came more quickly, where the rhythm of light and dark was compressed compared with today. Life evolved under a planet whose clock has been slowly stretching. The 24-hour day is not an eternal law. It is the current chapter in a long rotational history. And because Earth's rotation is not perfectly steady, our timekeeping systems have had to adapt. Atomic clocks are extremely stable, far more stable than Earth's spin. They define seconds with astonishing precision, based on the behavior of atoms rather than the turning of the planet. But the world people live in still cares about the sun being roughly where clocks say it should be. That is why systems like leap seconds have been used. Small adjustments added to keep civil time from drifting too far away from Earth's actual rotation. In other words, our clocks became so good that the planet itself began to look slightly irregular by comparison. There is something almost funny and humbling in that. For most of human history, the sky was the clock. Now our clocks are precise enough to correct the sky, or at least to correct our relationship to it. Yet this does not make the planet flawed, it makes it real. A perfect 24-hour day would belong to a simplified model, not to an ocean-covered, atmosphere-wrapped, moon-pooled, internally shifting world. Earth is alive with motion, not biologically alive as an organism, but dynamically alive as a physical system. Its spin carries the memory of impacts, tides, mass movements, and deep planetary structure. Its day is shaped by astronomy, geology, oceanography, and atmospheric motion all at once. The simple sunrise outside your window is the visible surface of an enormous hidden calculation that no one had to design. Earth turns, but it wobbles slightly. Earth orbits, but not in a perfect circle. Earth faces the sun, but with a tilted body. Earth keeps time, but not like a machine built in a factory. It keeps time like a planet, and maybe that is the deeper lesson hidden inside the ordinary clock. Human life depends on smooth units, seconds, minutes, hours, schedules, calendars. We carve time into clean boxes so we can meet each other inside it. But the natural world underneath those boxes is more fluid. A day is not one simple thing. It is a relationship between rotation, orbit, sunlight, stars, gravity, oceans, and the choices humans make when they decide how to measure. The 24-hour day is real as a useful average, but it is not the raw heartbeat of Earth in every instant. It is a negotiated peace between the irregular sky and the human need for order. So the next time midnight passes on a clock or morning light enters your room, remember that you are not riding a perfect timepiece. You are riding a rotating planet whose days breathe, drift, lengthen, and vary in tiny ways. The clock says 24 hours because civilization needs a steady promise. Earth answers with something more subtle, almost 24 hours, averaged, adjusted, and carried through space by a world still turning under the pull of the moon, the warmth of the sun, the motion of oceans, and the deep, quiet restlessness of its own body. The moon helps stabilize Earth's tilt. The moon is not just a pale ornament in the night sky. It is one of the quiet reasons Earth has kept a relatively steady posture while life learned how to endure the seasons. When you look at the moon, it is easy to think of it as distant and decorative, a glowing companion for poets, oceans, calendars, and sleepless windows. But gravitationally, it is much more than a beautiful disk. It is a stabilizer. Earth does not stand upright as it travels around the sun. Its axis is tilted by about 23.5 degrees, and that tilt is the main reason we have seasons. When one hemisphere leans toward the sun, it receives more direct sunlight and longer days. When it leans away, sunlight arrives more shallowly, and days shorten. Winter and summer are not caused by Earth being much closer or farther from the sun, in the simple way people sometimes imagine. They come mostly from the angle of the planet's body, from the way Earth carries itself through space. But a tilted spinning planet is not automatically stable forever. Other planets, the sun, and the shifting shape of Earth's orbit all tug gently on Earth over long periods of time. These tugs do not throw the planet around from one day to the next, but over thousands, millions, and billions of years, even small gravitational influences can matter. Earth's axis slowly wobbles, a motion called precession, like a spinning top tracing a circle as it turns. The moon's gravity plays a major role in that wobble. It pulls on Earth's equatorial bulge because Earth is not a perfect sphere. Its rotation makes it slightly wider around the middle. That pull helps set the rate at which Earth's axis precesses. And here is the subtle but important part. By influencing the speed of Earth's axial precession, the Moon helps keep Earth's tilt from wandering into more chaotic patterns caused by resonances with other motions in the solar system. In simple language, the Moon helps Earth's spin avoid dangerous long-term rhythms that could otherwise make the planet's tilt swing much more wildly. Without a large Moon, Earth's tilt might have varied far more dramatically over deep time, although scientists continue to model the exact range and behavior. Some studies suggest that without the Moon, Earth could experience larger and more chaotic changes in obliquity, the scientific word for axial tilt. It might not instantly tumble into disaster, and it would not become unlivable overnight, but its climate history could be less steady, less predictable, and more extreme. Imagine a planet whose tilt shifts greatly over geological time. The poles might sometimes lean much more toward the sun, creating intense seasonal contrasts. Ice could spread differently. Tropical zones could shift. Long-term climate patterns could become more unstable. Regions that once had moderate seasons might face harsher swings. Life could still adapt in some scenarios, because life on Earth is astonishingly resilient. But adaptation would be asked to solve a much harder puzzle. Stability matters not because change is bad, but because too much unpredictable change can make long-term biological development more difficult. The Moon, then, has not frozen Earth perfectly in place. Earth's tilt still changes slightly over tens of thousands of years, moving within a modest range. These slow variations are part of natural climate cycles, along with changes in Earth's orbit and the timing of seasons. But compared with what might happen on a moonless Earth, our axial behavior has been relatively gentle. The Moon acts like a gravitational hand resting lightly on the shoulder of a spinning planet, not holding it still, but keeping its motion from becoming too erratic. This is one reason our Moon is so unusual and important. Compared with Earth, the Moon is large. Many planets have moons, but Earth's Moon is massive relative to its planet in a way that gives it a powerful role in Earth's rotational story. The leading explanation for its origin is that, early in Earth's history, a Mars-sized body likely struck the young Earth, throwing material into orbit that eventually formed the Moon. That ancient collision was violent beyond imagination, but from its aftermath came a companion that would shape tides, slow Earth's rotation over time, and help stabilize the planet's tilt. A catastrophe became a rhythm, an impact became a partnership, and through that partnership, Earth's environment may have become a little more hospitable to complex life. The Moon also raises tides, and tides have their own long story, affecting coastlines, marine environments, Earth's rotation, and the gradual movement of the Moon away from Earth. But its role in stabilizing tilt is quieter, less visible, and perhaps more profound. You do not see axial stability when you watch moonlight on a rooftop. You do not feel gravitational precession when you walk through autumn air. Yet the seasons you know, the agricultural patterns human cultures depended on, the relative regularity of climates over long spans, and the familiar rhythm of light across the year are all connected to Earth's tilted posture, being held within a life-friendly range. The Moon does not create the seasons, but it helps keep the stage on which seasons unfold from becoming wildly unstable. That distinction matters. The sun provides the light. Earth's tilt distributes it unevenly across the year. The Moon helps keep that tilt from drifting too far into chaos. In this sense, the Moon is not the main actor, but a hidden stagehand, adjusting the balance of the scene so the play can continue. And there is something deeply humbling about that. We often think of life as something that happens only on Earth's surface. Soil, water, air, cells, roots, animals, weather. But the conditions that allow life to persist are also written in celestial mechanics. The angle of a planet, the pull of a moon, the rhythm of a wobble, the shape of an orbit. These quiet astronomical details can influence whether climates remain steady enough for forests to spread, oceans to circulate in familiar ways, ice ages to come and go within limits, and species to adapt rather than be constantly overwhelmed. The story of life is not only biology, it is also geometry, gravity, timing, and companionship. Every spring, every winter, every migration, Every harvest, every tree ring recording a season is part of a larger cosmic arrangement. The moon is woven into that arrangement not as decoration, but as structure. If it were much smaller, much farther away, or absent entirely, Earth might still be Earth in name, but its long-term behavior could be less kind. The night sky would be darker. The tides would be different. The length of days would have followed a different history, and the planet's tilt might have wandered with a freer, more dangerous hand. So when you see the moon hanging above the horizon, try to imagine what it is doing beyond beauty. It is pulling on oceans, yes, but also on the shape of Earth itself. It is helping guide the slow wobble of our axis. It is participating in a gravitational balance so patient that no human lifetime can watch it unfold directly. It has been there through the rise and fall of species, through ice ages and warm periods, through forests, reefs, deserts, and the first eyes that ever looked up and noticed its light. The moon does not speak, but its presence has helped keep Earth's seasons from becoming a wilder language. And maybe that is why moonlight feels so calm. Not because the moon is gentle in some sentimental way, but because its gravity has helped give our planet a kind of long, steady breathing. Above you, it looks like a silent companion. Beneath that silence, it is part of the reason Earth has been able to keep leaning toward the sun, away from the sun and back again, in a rhythm stable enough for life to learn the music. Some ice can be hot. The word ice makes you imagine coldness, but in the deeper language of physics, ice does not always mean something freezing. It means water locked into a solid structure, and under the right pressure, that solid can exist at temperatures that would normally seem impossibly hot. This is where one of the most familiar substances in your life becomes strange again. You know water as something simple. It flows from a tap, freezes in a tray, melts in a glass, boils in a kettle. In ordinary life, ice belongs to winter, refrigerators, glaciers, snowfields, and the sharp feeling of cold against your skin. At normal air pressure, the rule feels clear. Cool water down enough and it becomes ice. Warm it back up and it melts. But that rule is not a universal law for every possible place in the universe. It is only the version you live with at Earth's surface, under the gentle pressure of the atmosphere around you. Change the pressure enough, and water begins to reveal a hidden personality. Its molecules can be forced into different arrangements, different crystal structures, different forms of solid water that do not behave like the ice in your drink. Scientists have discovered many kinds of ice, not just one. Ordinary ice, the kind that floats in your glass, has a loose crystal structure that makes it less dense than liquid water, which is why ice floats. That single fact is already unusual because most solids sink in their liquids. But ordinary ice is only one chapter in water's story. Under high pressure, the molecules can pack together more tightly, forming phases known by names like Ice 2, Ice 3, Ice V, Ice Ves, Ice 7, and beyond. These are not different chemicals. They are still water, still made of hydrogen and oxygen, but the molecules are arranged differently, like the same bricks built into entirely different buildings. Some of these high-pressure ices can remain solid at temperatures much higher than the melting point of ordinary ice, because pressure changes the balance between solid and liquid. When pressure squeezes the molecules hard enough, it can favor a dense solid arrangement even when heat is trying to make them move freely. In everyday life, heat loosens structure, but pressure can force structure back into place. This is the key to understanding how ice can be hot. Temperature is about the motion and energy of particles, while solidness is about structure. A material can be very energetic and still be held in an ordered form if the surrounding pressure is extreme enough. So, hot ice is not a contradiction once you leave the conditions of your kitchen. It is a reminder that matter does not have one personality. It has many, depending on the environment. One of the most fascinating forms is Ice 7, a high-pressure phase that can exist under conditions far beyond normal surface life. It has been studied in laboratories using tools like diamond anvil cells, where tiny samples are squeezed between diamonds to create pressures similar to those deep inside planets. Diamonds are used not for beauty, but because they are incredibly hard and transparent, allowing scientists to compress a sample and observe what happens. Under such pressures, water can become a solid even at temperatures where ordinary ice would have vanished instantly. Go even deeper into extreme conditions, and water becomes stranger still. Inside giant planets such as Uranus and Neptune, scientists believe water may exist in exotic forms, including a state called supersonic ice. This is not ice like a snowflake, and it is not liquid water like an ocean. In supersonic ice, the oxygen atoms can remain arranged in a solid-like lattice, while the hydrogen nuclei move more freely through that structure, almost like a fluid moving through a fixed framework. It is sometimes described as both solid and liquid in different ways at the same time, though even that description is only a rough bridge for the imagination. This state may exist at thousands of degrees under enormous pressure, which means it would be incredibly hot by human standards, and yet still partly structured like a solid. If you tried to touch it, you would not experience a strange warm snowball. You would be facing conditions that no human body could survive. This kind of hot ice belongs to planetary interiors, shock experiments, and high-pressure physics, not to ordinary hands. But its existence matters, because it may help explain the strange magnetic fields of ice giant planets. Uranus and Neptune do not have magnetic fields shaped exactly like Earth's. Their fields are tilted, offset, and irregular, and one possible part of the explanation involves electrically conductive layers of exotic water-rich material inside them. If supersonic ice conducts electricity because hydrogen ions can move through the oxygen framework, then deep hot ice may participate in generating planetary magnetism. In other words, a substance you associate with cooling a drink may, under cosmic pressure, help shape invisible magnetic worlds billions of kilometers away. That is the power of this idea. It takes something domestic and turns it planetary. It shows that the same water molecule can become a snowflake, steam, ocean, glacier, high-pressure crystal, or supersonic material depending on the forces around it. The identity of matter is not just what it is made of. It is also where it is and what conditions hold it. This is why the phrase "ice can be hot" is not a gimmick. It is a doorway into the phase behavior of matter. A phase is simply the form a substance takes under certain conditions: solid, liquid, gas, plasma, or more unusual states. We often learn these as if they are simple categories, but nature treats them as possibilities on a landscape. Temperature pushes matter one way, pressure pushes it another. Molecular shape, bonding, and environment all matter. For water, this landscape is especially rich. The familiar version of ice is delicate and open, full of tiny spaces in its crystal structure. High-pressure ice is more compact, squeezed into arrangements ordinary ice could never adopt. As pressure rises, water molecules are forced closer, and the usual rules your senses learned begin to fail. It is almost like meeting someone you thought you knew completely, only to discover they have lived many lives in places you have never visited. This also changes how you think about coldness itself. Cold is not what makes something ice in every situation. Cold helps ordinary water freeze at the surface of Earth, but solidness can also come from pressure. In some extreme settings, pressure can dominate the story so strongly that heat cannot easily melt the structure. So the word ice becomes less about the feeling on your skin and more about the arrangement of water under constraint. That is difficult to accept because language trains intuition. You hear ice and your body remembers cold. Science asks you to loosen that memory. It asks you to imagine matter not as fixed labels, but as behavior under conditions. A material is not only a thing, it is a response. Water responds to pressure, heat, and environment by becoming many versions of itself. And perhaps that is why water keeps appearing in so many deep questions about planets and life. It is simple enough to be common, but complex enough to surprise us again and again. On Earth's surface, it softens landscapes, carries nutrients, fills cells, and falls as rain. Deep inside planets, it may become compressed into forms that feel alien. In laboratories, it can be pushed into states that reveal how molecules behave when the world around them becomes extreme. The ice in your freezer and the hot ice inside a giant planet are not opposites. They are relatives separated by pressure. One forms in the quiet cold of daily life. The other may form in the crushing depths of worlds where the word weather means something completely different. So the next time you hear ice crack in a glass, let the sound become a small reminder of a much larger truth. You are hearing only the gentlest version of solid water, the version allowed by Earth's surface. Far beyond that familiar form, water has hidden architectures, dense, compressed, strange, sometimes hot enough to make ordinary ice seem like a fragile childhood memory. Some ice can be hot because the universe is not obligated to obey the meanings humans attach to words. It follows conditions, it follows pressure, it follows structure, and in those hidden conditions, even water, the substance you drink, wash with, cry through, and watch fall from clouds, can become something almost unrecognizable. A burning solid, a planetary layer, a secret architecture of heat held in place by the weight of worlds. Earth is not a perfect sphere. The planet beneath your feet looks perfectly round from space, but that smooth blue sphere is actually a slightly squashed, uneven, slowly shifting body shaped by rotation, gravity, rock, water, ice, and time. From far away, Earth appears almost flawless, a bright marble suspended in darkness, with white clouds curling over blue oceans and brown-green continents. That image is true, but it is not complete. Earth is round in the broad sense, but it is not a perfect sphere, not the kind of mathematical ball you might hold in your imagination, where every point on the surface sits the same distance from the center. The first reason is rotation. Earth spins once each day, and because of that spin, the planet bulges outward slightly at the equator and flattens slightly at the poles. Imagine shaping a soft ball while it turns. The middle wants to push outward a little, while the top and bottom become slightly compressed. Earth is not soft like clay on human timescales, but over planetary history, its material can respond to forces, and its rotating shape reflects that. The equatorial radius is about 21 kilometers larger than the polar radius, which means if you could measure from Earth's center to sea level at the equator, then measure from Earth's center to sea level at the poles, the equatorial distance would be noticeably greater by scientific standards, though still tiny compared with Earth's whole size. This shape is called an oblate spheroid, almost a sphere, but slightly wider around the middle. To your eyes, the difference is invisible because Earth is enormous and the distortion is subtle. If you saw a small model scaled accurately, it would still look nearly round. But precision matters because satellites, navigation systems, maps, astronomy, and geophysics all need to understand Earth as it really is, not as a perfect ball. This equatorial bulge also affects gravity. At the equator, you are slightly farther from Earth's center than you would be at the poles, and the planet's rotation creates a small outward effect. Together, these make effective gravity a little weaker at the equator than at the poles. You would not feel a dramatic difference in daily life, and you would not suddenly become weightless by traveling south or north, but precise measurements can detect it. A scale that is extremely sensitive would not give exactly the same reading everywhere on Earth, even if your mass stayed the same. Your weight is not only about you, it is also about where on the planet you stand. But Earth's imperfection goes beyond the equatorial bulge. The surface is covered with mountains, trenches, plateaus, ocean basins, ice sheets, valleys, volcanoes, and deep structures hidden beneath the crust. Mount Everest rises high above sea level, while the Mariana Trench sinks deep below it. Yet even these dramatic features are small compared with Earth's full radius. If Earth were shrunk to the size of a classroom globe, the tallest mountains and deepest trenches would be barely noticeable to touch. The planet feels rugged to us because we are small. To space, it is smoother than our local experience suggests. And still, smooth does not mean perfect. The deeper and more accurate way to describe Earth's shape is the geoid, a model of what global mean sea level would look like if oceans could extend through the continents, shaped only by gravity and rotation, without tides, winds, currents, or weather. The geoid is not a simple sphere. or even a perfect oblate spheroid. It has gentle rises and dips, because Earth's gravity is not exactly the same everywhere. Gravity changes slightly depending on how mass is distributed inside the planet. Dense rock, mountain roots, ocean trenches, mantle structures, and other hidden variations create tiny differences in the gravitational field. These differences shape where level actually is. Sea level is not just a flat height wrapped around Earth. It follows an invisible gravitational surface. In some regions, because of the mass beneath, the ocean surface naturally sits a little higher or lower relative to a simple mathematical shape. This does not mean water forms strange visible hills like mountains in the sea. The slopes are extremely gentle over huge distances, far too subtle for the eye. But satellites can measure these variations, and those measurements reveal Earth as a lumpy gravitational body, not a perfect sphere. This is why mapping Earth accurately is so difficult. A map is not just a drawing, it is a compromise. Because Earth is curved and irregular, turning it into a flat map always distorts something. Size, shape, distance, or direction. The planet's not quite spherical form makes geodesy, the science of measuring Earth, essential. Engineers, pilots, oceanographers, surveyors, climate scientists, and spacecraft operators all depend on careful models of Earth's size, shape, gravity, and rotation. When you use a navigation app, when a plane crosses an ocean, when a satellite observes sea level rise, when scientists track melting ice or shifting groundwater, they are not relying on a childhood idea of Earth as a perfect ball. They are working with a planet that bulges, wobbles, flexes, and carries uneven mass. Earth is also not fixed forever in one shape. It changes slowly. Tectonic plates move, mountains rise and erode, glaciers press down on land, and when ice melts, land can rebound upward over thousands of years, a process still happening in places once covered by massive ice sheets. Earthquakes can shift mass and alter the planet's shape by tiny amounts. Large amounts of water can move between oceans, ice, groundwater, and atmosphere. The planet breathes through geological time, not like an animal, but as a physical system constantly redistributing material. Even the poles do not stay perfectly fixed relative to Earth's surface. The rotation axis can wander slightly, influenced by mass movements within the planet and across its surface. So Earth is not only imperfect in shape, it is dynamically imperfect. It is always being revised. The oceans smooth some of this complexity, but they also respond to forces of their own. Winds push water, currents redistribute heat and mass. Tides raised by the moon and sun lift and lower sea surfaces. Atmospheric pressure can press down on the ocean in one region more than another. So the sea surface you see from a beach is not the pure geoid in action. It is the geoid plus weather, currents, tides, temperature, salinity, and motion. The calm horizon may look like a simple line, but beneath that line is a world of moving forces. And this is what makes Earth's shape so humbling. The planet gives us a simple appearance because we need simple appearances to live, but the deeper reality is layered. A perfect sphere would be easy to imagine, easy to draw, easy to teach. The real Earth is more interesting. It is round enough to look serene from space, flattened enough for physics to notice, rugged enough for mountains and trenches to shape human history, uneven enough in gravity to require delicate measurement, and alive with slow changes that continue whether anyone watches or not. Even the idea of down depends on this complexity. Down does not always mean toward a perfect center in a simple geometric sense. Locally, down follows gravity, and gravity follows Earth's mass distribution and rotation. A plumb line, hanging freely, points along the local direction of effective gravity, which can differ slightly from what a perfect sphere model would predict. This means the world you stand on is not only physically uneven, the invisible direction of straight down is subtly shaped by the planet's hidden interior. Your body never notices most of this because life happens at human scale. The ground feels flat, the horizon looks stable, a mountain feels enormous, a valley feels deep, a globe looks round. All of these are valid experiences, but science allows you to zoom out and zoom in at the same time, to see that the ground beneath you belongs to a rotating, bulging, gravitationally textured object whose shape is a record of motion and matter. Earth's imperfection is not a flaw. It is evidence of its history. A perfect sphere would be almost lifeless as an idea, untouched by spin, tides, heat, geology, impacts, oceans, and internal structure. Earth's real shape tells you that it has been acted on, molded, stretched, lifted, eroded, and balanced by forces over billions of years. It is not a polished ornament. It is a planet with memory in its form. So when you see the famous blue globe floating in space, do not stop at the beauty of the sphere. Look deeper into the almost hidden truth behind it. The equator is slightly swollen, the poles slightly flattened, the gravity field gently uneven, the sea level surface subtly warped, the crust restless, the interior layered and moving, the surface reshaped by ice, water, heat, and stone. Earth is not perfect, and that is precisely why it feels real. It carries the marks of its own becoming. The planet beneath you is not a flawless ball. It is a vast, turning body, rounded by gravity, widened by rotation, wrinkled by geology, and softly uneven in ways only careful instruments can fully reveal. And perhaps there is something comforting in that. Even the world that holds you is not perfect. It does not need to be. Its slight imbalance, its hidden irregularity, its patient corrections and distortions are part of what make it Earth. Not an ideal shape in empty space, but a lived-in planet carrying oceans, continents, storms, mountains, and every quiet footstep ever placed upon its uneven surface. Your skeleton is constantly being rebuilt. The bones holding you upright are not silent beams left inside you at birth. They are living structures being broken down, renewed, repaired, and reshaped while you walk through life feeling solid. It is easy to imagine the skeleton as the body's scaffolding, a dry white frame hidden under muscle, something passive, hard, and finished. But real bone is not dead architecture. It is active tissue, threaded with blood vessels, filled with cells, responsive to pressure, hormones, nutrition, injury, age, and movement. Every step you take sends tiny mechanical signals through your bones. Every time you lift a bag, climb stairs, stand, run, or even hold your posture against gravity, your skeleton receives information about what kind of body it needs to become. Bone is constantly asking a quiet question. Where should I become stronger? Where can I afford to be lighter? Where has damage appeared? Where does the body need minerals? Where must the structure be protected? Inside this process are specialized cells working like a hidden maintenance crew. Osteoclasts break down old or weakened bone, dissolving mineral and clearing space. Osteoblasts build new bone, laying down collagen and helping mineral crystals harden into strength. Osteocytes, mature bone cells embedded inside the mineral structure, act like sensors, detecting strain and helping coordinate the remodeling process. This does not happen randomly. It happens in cycles across millions of tiny sites, so that your skeleton can repair microscopic damage before it becomes a serious fracture, adapt to the forces of your life and help regulate minerals like calcium and phosphorus that your nerves, muscles, blood and cells need to function. This is one of the most surprising things about bone. It is not only a support system, it is also a mineral bank. Most of the body's calcium is stored in bones and teeth, and your blood calcium level must be kept within a narrow range for muscles to contract, nerves to signal, and the heart to beat properly. If calcium in the blood drops too low, the body can draw from bone. If conditions allow, it can store minerals back into bone. So your skeleton is both structure and reserve, both pillar and pantry, both the shape that holds you and the storehouse that quietly supports your chemistry. But this renewal has a rhythm that changes across life. In childhood and adolescence, bone building is intense because the body is growing, lengthening, thickening, and preparing for adulthood. During these years, nutrition, movement, hormones, sunlight-related vitamin D production, and overall health all influence how strong the skeleton becomes. Peak bone mass, the greatest amount of bone a person builds, is usually reached in early adulthood. And it matters because it becomes part of the reserve you carry into later life. After that, remodeling continues, but the balance between building and breakdown can shift. With aging, certain hormonal changes, reduced activity, poor nutrition, illness, smoking, some medications or other factors, bone loss may begin to outpace bone formation. When this becomes significant, bones can become more fragile, a condition known as osteoporosis. The frightening part is that weak bones may not hurt at first. You can feel normal while the inner architecture is becoming thinner and more porous. Then a fall, a twist, or even ordinary stress can cause a fracture that would not have happened in stronger bone. This is why the skeleton teaches a quiet lesson about hidden health. What feels strong from the outside may still need care beneath awareness. Bone strength is not only about hardness. It depends on density, architecture, quality of collagen, mineral content, and the way tiny internal struts are arranged. Some bone is compact and dense, forming strong outer layers. Some is spongy, a lattice-like structure found near the ends of bones and inside vertebrae, designed to be light but supportive. This inner lattice can change based on stress. The body does not want to waste energy maintaining bone where it is not needed, so bones adapt to use. Astronauts in microgravity can lose bone mass because their skeletons are no longer loaded by body weight in the usual way. On Earth, weight-bearing activity and resistance exercise helps signal bones to maintain or increase strength. This does not mean every person should push dangerously or ignore medical limits, but it does mean movement is a language bone understands. A couch, a bed, and a chair ask less of the skeleton. Walking, lifting, balance, and impact within safe limits tell bone, stay ready, stay strong. In that sense, the skeleton listens to your life more than you realize. It records use, disuse, injury, recovery, and time in its structure. Even a fracture reveals bone's living nature. When a bone breaks, it does not heal like a cracked stone glued back together from the outside. Blood vessels and cells rush into the damaged area. A clot forms. Inflammation begins the cleanup. A soft callus develops, then a harder callus. And over time, the bone remodels, reshaping the repair so it becomes stronger and more aligned with the forces placed upon it. The healing can take weeks to months depending on the bone, the break, age, blood supply, health, and care, but the principle is astonishing. Bone can rebuild itself after being broken. It can bridge damage, restore continuity, and gradually erase the rough evidence of injury through remodeling. This is not magic. It is biology with patience, but perhaps the deepest wonder is that the skeleton is not just a frame under the body. It is also part of the body's inner life. Bone marrow inside many bones produces blood cells, red blood cells that carry oxygen, white blood cells that help defend against infection, and platelets that help with clotting all arise from stem cells in marrow. So the skeleton is not merely holding your blood vessels in place. In many regions, it is helping create the blood itself. The same bones you think of as hard and silent contain spaces where the body is continually making new cellular life. Your skeleton is therefore both stone-like and fertile, both rigid and generative. It protects the brain through the skull, the heart and lungs through the rib cage, the spinal cord through the vertebrae. It allows movement by giving muscles levers to pull against. It stores minerals, makes blood, senses strain, repairs cracks, and changes with your habits. It is far more alive than its dry museum image suggests. And this changes how you might feel about your own body. You are not simply wearing down like an old machine. Parts of you are constantly responding, renewing, negotiating with time. Of course, renewal is not perfect, and the skeleton can weaken, deform, ache, or break. Biology is powerful but not invincible. Still, the fact that your bones are working right now, adjusting in darkness, replacing old material, repairing microscopic stress, and helping maintain the chemistry of your blood, means that stillness is not inactivity. Even when you sit quietly, your skeleton is not merely waiting. It is participating in the ongoing construction of you. So the next time you feel your feet meet the ground, or notice the shape of your wrist, your jaw, your spine, your ribs rising with breath, remember that beneath the softness of skin and muscle is not a dead framework, but a living memory of pressure and repair. Your skeleton is constantly being rebuilt, not so dramatically that you notice it day by day, but faithfully enough that you can stand, heal, carry weight, and move through the world with a sense of form. Bone is the body's quiet promise that strength does not mean never changing. Sometimes strength is the ability to be remade, grain by grain, cell by cell, without losing the shape that lets you rise. Your stomach gets a new lining every few days. The acid inside your stomach is strong enough to help dissolve food, yet the organ survives because its inner surface is not a permanent wall. It is a living shield that keeps renewing itself before digestion can turn against the body. This sounds almost alarming when you first slow down and picture it. Every day, your stomach receives food that may be rough, hot, cold, spicy, fatty, fibrous, acidic, or full of unfamiliar chemistry. It churns that food with muscular waves, mixes it with digestive juices, and releases hydrochloric acid powerful enough to create an environment where many microbes cannot easily survive and where proteins begin to unfold. It also releases enzymes such as pepsin, which help break proteins into smaller pieces. In simple terms, the stomach is built to be chemically harsh. It is not a gentle bowl. It is more like a controlled storm chamber, a place where food is softened, sterilized in part, mixed, and prepared for the next stages of digestion. And yet the stomach is made of living tissue. So the question becomes strange and necessary. Why does the stomach not digest itself? The answer is not one single trick, but a layered defense system. And one of its most important features is renewal. The surface of the stomach is lined by epithelial cells that do not last forever. Many of the surface mucous cells are replaced rapidly, often over a span of only a few days, while deeper specialized cells can live longer. So it is not accurate to imagine the entire stomach being completely rebuilt from top to bottom every few days in one dramatic event. The more accurate truth is that the stomach's exposed inner surface is constantly being refreshed, especially the cells most directly facing acid, friction, and digestive stress. These cells produce mucus, a slippery protective layer that coats the stomach lining. This mucus is not just slime in the simple sense. It is a carefully maintained barrier, thick enough to slow acid from reaching the cells beneath it. Within that mucus, bicarbonate helps neutralize acid near the stomach wall, creating a tiny protective zone where the pH is much less harsh than the liquid in the stomach's central cavity. So the stomach contains acid, but the lining lives behind a chemical shield. The acid helps digest food in the lumen, while the mucus bicarbonate layer protects the tissue from that same acid. It is like having a fire inside a room whose walls are continuously coated, repaired, and watched for damage. Beneath the surface, stem cells and gastric glands help produce new cells that move upward to replace old or damaged ones. This turnover is essential because the stomach lining is constantly exposed to stress. Acid, enzymes, mechanical mixing, alcohol, certain medications, infections, bile reflux in some cases, and the simple wear of daily digestion. The body does not try to make one lining last forever. It uses a better strategy. Replace the most exposed parts again and again. This constant renewal is one reason the stomach can continue working for decades, meal after meal, without destroying itself under normal conditions. But the balance is delicate. If acid production becomes too high, if mucus protection weakens, if blood flow to the lining is reduced, if certain anti-inflammatory medicines interfere with protective prostaglandins, or if the bacterium Helicobacter pylori infects the stomach and disrupts the protective environment, damage can occur. This damage can lead to inflammation or ulcers, places where the lining is injured deeply enough that the stomach's own acid and enzymes become dangerous to its tissue. For a long time, people believed ulcers were mostly caused by stress or spicy food. But modern medicine showed that H. pylori infection and certain medications, especially non-steroidal anti-inflammatory drugs like ibuprofen or aspirin when used in risky ways, are major causes. Stress and diet can affect symptoms for some people, but they are not the whole explanation. This is a powerful reminder that the stomach's survival depends on balance, not toughness alone. Its defenses include mucus, bicarbonate, rapid cell renewal, good blood supply, tight connections between cells, immune responses, and careful regulation of acid. If the balance holds, digestion continues quietly. If the balance fails, the same chemistry that helps feed you can injure you. The stomach also teaches something deeper about what strength really looks like inside the body. We often imagine strength as hardness, as something rigid that resists change. But the stomach survives through softness, moisture, flexibility, and constant renewal. Its lining is not a stone wall. It is more like a living shoreline, continually washed by harsh waves, continually rebuilding the edge where the waves strike. The cells that face the acid are not meant to be immortal. Their short life is part of the design. They serve, protect, wear down, and are replaced. Behind them, new cells rise into place. This is not wasteful. It is how living systems remain whole in dangerous conditions. The stomach accepts that damage at the microscopic level is inevitable, so it makes repair part of normal life, rather than waiting for disaster. And in that sense, your stomach is doing something quietly profound every time you eat. It is not only breaking food down, it is protecting the body from the breakdown process itself. It is controlling a force that could harm it, using that force just long enough to help transform the outside world into usable nourishment. The bread, fruit, rice, vegetables, meat, or soup you swallow enters a chamber where chemistry and movement begin the work of turning meal into energy, building material, and life. Meanwhile, the lining keeps renewing, not dramatically, not visibly, not with any sensation you can easily notice, but faithfully. You do not feel each old surface cell detach. You do not feel each new cell take its place. You simply feel hunger, fullness, comfort, nausea, appetite, warmth after a meal, or the quiet return of energy. Beneath those ordinary feelings is a hidden cycle of protection. The stomach is constantly negotiating with its own power. It must be acidic enough to digest, but protected enough to survive. It must be strong enough to churn, but sensitive enough to signal discomfort when something is wrong. It must welcome the outside world into the body, but not let that world harm the body's inner boundary. So the next time you eat, imagine the stomach not as a passive bag, but as a living laboratory with self-repairing walls. Acid gathers, enzymes activate, muscles fold and mix the meal. Mucus spreads like a protective mist. Bicarbonate softens the danger near the surface. Blood delivers oxygen and nutrients to the tissue, and new cells quietly replace the old. Your stomach gets a new exposed lining over and over because life sometimes survives not by avoiding harshness, but by learning how to renew itself faster than harshness can win. And perhaps that is the soft lesson hidden in digestion. Even the parts of you built to handle acid are protected by tenderness, by layers, by repair, by the wisdom of letting worn-out surfaces go and growing new ones in their place. Your bones are stronger than concrete by weight. A bone in your leg can feel fragile when you imagine it breaking, yet gram for gram, healthy bone is an astonishing engineering material, often stronger than concrete by weight because it is not just hard, it is intelligently built. Concrete seems like the obvious symbol of strength. It holds buildings, bridges, sidewalks, tunnels, and entire cities in place. Bone, by contrast, is hidden under skin, associated with injury, pain, x-rays, and the fear of a fall. But strength is not only about how heavy or massive something looks. Strength also depends on structure, flexibility, composition, direction of force, and how much weight the material carries for the strength it provides. Concrete is excellent under compression, meaning it can handle being squeezed, but it is much weaker when pulled or bent, which is why buildings often use reinforced concrete with steel inside. Bone is different. It is a natural composite, a material made by combining different ingredients so that each one compensates for the weaknesses of the other. The mineral part of bone, mostly a calcium phosphate crystal called hydroxyapatite, gives it hardness and resistance to compression. The protein part, especially collagen, gives it flexibility and toughness. helping it absorb energy instead of shattering like dry chalk. If bone were only mineral, it would be hard but brittle. If it were only collagen, it would be flexible but not rigid enough to hold you upright. Together, they create something more subtle than stone, a material that can be firm, light, slightly flexible, and surprisingly resistant to everyday stress. This is why the phrase, "stronger than concrete by weight," needs to be understood carefully. Bone is not stronger than concrete in every possible situation, every direction, or every condition. A wet, living femur, a dry old bone, a thin rib, a dense section of cortical bone, and the spongier trabecular bone inside joints do not all behave the same way. Concrete itself also varies depending on mixture, curing, reinforcement, and quality. But when scientists and engineers compare strength relative to weight, healthy compact bone is remarkable. It can handle large forces while remaining much lighter than a solid block of mineral material. Your skeleton has to solve a problem concrete usually does not. It must support a moving animal without making that animal too heavy to move. If your bones were as dense and heavy as stone columns, you might be strong, but you would be slow, exhausted, and unable to run, jump, climb, balance, or respond quickly. Evolution did not build your skeleton like a bunker. It built it like a living bridge. Light where it can be light, dense where it must be dense, curved where curves distribute stress, hollow where hollow shapes can save weight, and internally patterned where forces need guidance. A long bone, such as the femur, is not a solid rod from end to end. Its shaft is mostly compact bone arranged around a central cavity, and this tube-like shape is extremely efficient. Engineers understand this well. A hollow tube can resist bending very effectively while using less material than a solid rod of the same outer diameter. The strength does not come only from the amount of matter, but from where the matter is placed. Put material farther from the center, and it can resist bending better. Your bones learn this lesson not from textbooks, but from millions of years of biological refinement. Near the ends of long bones, where forces arrive from joints in many directions, the structure changes. Inside, trabecular bone forms a lattice of tiny struts and plates, arranged along lines of stress. It may look delicate, almost sponge-like, but it is not random. Its architecture helps spread forces, absorb shock, and reduce weight. In places like the hip, vertebrae, and ends of bones, this internal scaffolding is part of why the skeleton can be both strong and light. Concrete, by comparison, is usually poured into shapes designed by human engineers. Bone is grown into shapes designed by use, inheritance, and adaptation. It carries the memory of load in its form. This is why strength in bone is directional. Bone is anisotropic, meaning it has different strength depending on the direction of the force. It is built to handle the kinds of loads your body normally experiences. Compression when you stand, bending when you walk, twisting when you turn, impact when you jump, tension where muscles pull through tendons. But if force arrives in the wrong way, too suddenly, too sharply, or at a vulnerable angle, bone can break. This does not make bone weak, it makes it real. Even the best engineering materials have limits, and bone's limits are shaped by its job. It must be strong enough to protect organs and carry weight, light enough for movement, tough enough to resist cracking, and adaptable enough to respond to life. One of the most elegant features of bone is toughness. Hardness and toughness are not the same. A glass object can be hard but not tough. It resists scratches, but it may shatter when struck. Rubber can be tough in some ways but not hard. Bone sits between these extremes. Its collagen fibers help slow the spread of cracks. Its mineral crystals provide stiffness. Its microscopic structure contains layers, boundaries, tiny channels, and interfaces that can deflect cracks, absorb energy, and keep small damage from becoming instant failure. In other words, bone does not merely resist force. It manages force. It bends slightly. It distributes stress. It sacrifices microscopic regions before allowing catastrophic collapse. This is a lesson human materials science continues to study. Nature often achieves strength not through one perfect substance, but through hierarchy. Bone has structure at many scales, from molecules to fibers, from microscopic units to the whole shape of the skeleton. At each scale, the design contributes something. The mineral gives hardness. Collagen gives resilience. The microscopic arrangement guides cracks. The hollow geometry saves weight. The whole bone shape fits the body's movement. Strength is not located in one place. It is spread through layers of organization. This is why bone can seem almost contradictory. It is rigid, but not completely stiff. It is light, but not flimsy. It is strong, but not indestructible. It is mineralized, but alive. And because it is alive, it can do what concrete cannot do by itself. Sense stress, repair small damage, and change over time. A sidewalk does not strengthen itself because people walk over it. A concrete pillar does not notice a microscopic crack and send cells to remodel the region. Bone does. This does not make bone invincible, and it does not mean every bone stays strong without care. Nutrition, hormones, age, activity, disease, medications, and genetics all affect bone quality. Bone can become weaker if it loses mineral density, if its internal architecture thins, if collagen quality changes, or if it is not loaded enough through safe movement. But the healthy skeleton is not a passive frame waiting to fail. It is an active material system, and its strength is tied to life itself. This also explains why bones can be both powerful and vulnerable in emotionally surprising ways. A femur can withstand forces many times body weight during running or jumping, yet a sideways fall in an older person with fragile bones can cause a hip fracture. A tiny bone in the wrist can break from a sudden impact, while the skull can protect the brain from many ordinary bumps because of its curved shell-like shape. Bone strength is always about context. The kind of bone, the angle of force, the speed of impact, the health of the tissue, and the geometry of the structure. So the statement, "bones are stronger than concrete by weight," should not make you imagine bone as a superhero material that cannot break. It should make you appreciate how refined it is. Concrete is heavy strength. Bone is efficient strength. Concrete stands still. Bone moves. Concrete supports buildings by resisting gravity in fixed shapes. Bone supports a living body that twists, runs, heals, grows, balances, and changes direction. Concrete often needs steel to handle tension well. Bone carries its own reinforcement through collagen. Concrete cracks and remains cracked unless repaired from outside. Bone can respond from within, and maybe this is the deeper wonder. The strongest parts of you are not strong because they are unchanging or brutally hard. They are strong because they are balanced. Your bones are a compromise between stone and fiber, between weight and motion, between protection and lightness, between resistance and repair. They are not just the remains seen in museums or the white symbols of mortality. Inside you, bone is a living engineering achievement, holding up a conscious creature without making that creature feel like it is made of pillars. So the next time you stand, walk, lift, or simply feel the quiet support of your own body, remember that beneath you is not crude scaffolding. It is a lightweight architecture more elegant than concrete, a natural composite shaped by pressure, movement, and time. Your bones do not need to be massive to be strong. They only need to place strength where life needs it. And that is exactly what they have been doing, silently, since before you had words for standing. Glass is not a slow-moving liquid. The old window pane that looks thicker at the bottom is not slowly melting like frozen honey. It is holding the shape it was given. And the real mystery is not that glass flows, but that a solid can exist without the neat inner order we usually expect from solids. For a long time, people repeated the idea that glass is a slow-moving liquid, pointing to old church windows and antique panes that appear uneven, wavy, or thicker near the base. It is a tempting story because it feels almost magical. A cathedral window standing for centuries, its glass silently drooping under gravity, time made visible as a material sigh. But the evidence does not support that popular myth. Old glass is uneven mostly because of how it was made. Before modern flat glass manufacturing became precise, window glass was often produced by methods that left variations in thickness, bubbles, waves, ripples, and distortions. In one method, Molten glass could be spun into a disc and cut into panes, producing pieces that were not perfectly uniform. In another, cylinders of glass were blown, cut, reheated and flattened, again leaving imperfections. When builders installed these panes, thicker edges were often placed at the bottom for stability or simply by habit, which later made it look as if the glass had flowed downward over centuries. But if glass were truly flowing noticeably under its own weight at room temperature, we would expect clearer signs in many old glass objects: lenses losing precision, museum vessels slumping, ancient beads changing shape, thin glass shelves sagging in predictable ways. Instead, ordinary glass at room temperature is so rigid and its internal movement so slow that, on human historical timescales, it behaves as a solid. Not a perfect crystal, but a solid. And this is where the real science becomes more interesting than the myth. Most solids, you imagine, salt crystals, diamonds, metals in many forms, ice under ordinary conditions, have atoms or molecules arranged in repeating patterns, like a carefully tiled floor extending in 3 dimensions. Glass is different. Its atoms are arranged more like a frozen crowd than a marching army. They are not completely random in every possible way, but they do not form the long, repeating order of a crystal. This is why glass is called an amorphous solid. Amorphous simply means without a clear, repeating shape at the atomic scale. The atoms are locked into a disordered arrangement, somewhat similar to the structure of a liquid, but they are not free to move around like a liquid. Imagine a group of dancers suddenly frozen mid-motion, not lined up in rows, not organized into a formal pattern, but still held firmly in place. That is closer to glass than the idea of a liquid slowly sliding downward. To make common glass, materials such as silica-rich sand are heated until they melt into a hot liquid. If that liquid cools in a way that prevents its atoms from arranging into crystals, it becomes glass. The structure is trapped before it can settle into a regular pattern. This is why glass is sometimes described as a frozen liquid, or a supercooled liquid in a loose sense. But those phrases can mislead people. They are trying to describe the disordered structure, not claim that your window is actively flowing like syrup. The more careful description is that glass is a non-crystalline solid, formed through a glass transition. It does not freeze with a sharp melting point in the same simple way water becomes ice. Instead, as molten glass cools, it becomes more and more viscous, more resistant to flow, until molecular motion becomes so limited that the material is effectively solid. This transition is gradual, not a sudden snap from liquid to crystal. That gradual change is part of what makes glass scientifically fascinating. It occupies a strange middle ground in our categories. It is solid in everyday life, but its internal structure remembers something of the liquid it once was. It is hard, transparent, brittle, and stable, yet its atoms lack the tidy order found in crystals. When it breaks, it does not split along neat crystal planes. It fractures in sharp, curved patterns because its internal structure has no repeating grain guiding the crack in one preferred direction. That is one reason broken glass can be so dangerously sharp. The crack races through disorder, finding its path through a rigid but non-crystalline network. Transparency is another part of glass's quiet strangeness. Many solids are opaque because their electrons interact with visible light in ways that absorb or scatter it strongly. Common window glass allows much visible light to pass through because of the way its atomic structure and electronic properties interact with those wavelengths. It is not invisible because it has no substance. It is transparent because visible light can travel through it without being strongly absorbed. At the same time, glass can block or absorb other kinds of light, such as much ultraviolet radiation, depending on its composition. So glass is not simply clear matter, it is selective matter. It lets part of the world pass through while stopping other parts, which is why a window feels like absence, even though it is very much present. Your hand cannot pass through it. Sound changes when it meets it. Heat moves through it imperfectly, and light bends when it crosses it. The world outside reaches you through glass, but altered. This is why lenses, prisms, microscopes, telescopes, eyeglasses, cameras, and fiber optic cables can exist. Glass does not only separate spaces, it can shape perception. It can bend light, focus images, split colors, carry signals, and extend human sight from cells to galaxies. A material often mistaken for a slow liquid became one of the main reasons humans learned to see farther and smaller than our bodies ever could alone. And still, the myth persists because glass feels mysterious. It looks like something between states. It is hard like stone but born from melt. It is solid but disordered. It can be transparent like air but cut like a blade. It can survive for centuries, yet shatter in an instant. That combination makes it easy for the imagination to treat glass as unfinished, as if it never fully decided what it wanted to be. But the better lesson is not that glass is secretly liquid. The better lesson is that solid does not always mean crystalline, and matter has more ways to be stable than our simple categories suggest. A brick and a diamond and a window pane are all solid, but not in the same internal language. Some solids are orderly, some are disordered, some are tough, some are brittle, some conduct electricity, some insulate, some are opaque, some are transparent. The word solid hides a whole world of structures beneath it. Glass teaches this especially well because it is familiar enough to touch every day and strange enough to challenge the definitions we learned as children. It also reminds you how easily a beautiful explanation can spread even when it is wrong. The story of old windows flowing downward feels elegant, visual, and memorable, but the manufacturing explanation is more accurate. This matters beyond glass. Science often asks us to choose the less dramatic truth when the dramatic version is unsupported, and then rewards us by revealing that the real truth is deeper anyway. No, the glass in an old window has not been slowly dripping for centuries in any meaningful, everyday sense. But yes, it is a solid without crystal order. Yes, it began as a molten substance and became rigid through a gradual transition. Yes, its atoms are locked in a disordered arrangement that still challenges physicists and materials scientists. Yes, its apparent simplicity hides complex behavior that helped build modern civilization. And perhaps that is more wondrous than the myth. A slow liquid would be only a curiosity. Glass as an amorphous solid is a doorway into the hidden variety of matter itself. So the next time you look through a window, do not imagine it as a liquid pretending to be still. Imagine it as a frozen disorder, a transparent solid born from heat and arrested before it could become a crystal. Imagine ancient craft marks in old panes, not gravity pulling them downward, but human hands and old furnaces leaving their uneven signature. Imagine light passing through a rigid atomic network that has no repeating pattern, and yet holds together so faithfully that it can protect rooms, sharpen vision, carry information, and frame the sky. Glass is not a slow-moving liquid. It is something stranger. A solid that never became a crystal. A stillness made from interrupted motion. A clear wall that reminds you reality is often most fascinating when the popular myth breaks and the quieter truth is finally allowed to shine through.